to be just kind of a spot lump load on the system, and it was basically ignored. They slowly transitioned in using sequential components, so that was the positive sequence, but it was found that that was inadequate for a lot of the particular issues that arise in distribution systems, particularly with what we call unbalanced power flow. A lot of times you have either loads on a single phase of your system or they're not completely balanced, so over the course of your entire distribution feeder, things end up being not quite 120 degrees separated like they would be on a transmission system. So distribution system modeling, as I mentioned, this is a relatively new thing, 20 years if you want to call that new. Most of the analysis continues to be done at the transmission level. There's a lot of planning studies done by utilities and different entities on the transmission system, figuring out what the stability concerns are, how to effectively schedule power for whatever day of the week, things of that nature. On the distribution side, it's been forced more by the emerging technologies on the smart grid, if you will. A lot more emphasis on how the individual end uses are behaving, how the system as a whole is impacted by these new technologies, and what kind of benefits the distribution system can provide to the whole system. Before, the distribution system was looked at basically as, like I said, a static load that isn't varying and just something that's in there as a convenience to your model. Nobody was really concerned with any of the potential the distribution system had on your overall system. So the modeling of the distribution system is a little different than the transmission modeling. It starts out about the same way, but it gets into an order of complexity, I guess is the best way to mention it. And it says more detail, and a lot of your end-use loads will get into more detail than a typical transmission system model, but a lot of the fundamental difference comes into all of the loads are considered unbalanced on a distribution system, even if they aren't necessarily unbalanced. If you think about it, a balanced load where you're only representing it by the positive sequence components is basically a special case of an unbalanced load, just all of the unbalanced components happen to be the same. The other unique thing about distribution systems is a lot of times you'll have either a single or a two-phase lateral going down branches of your feeder. That's not common inside transmission systems. It's almost always the full three-phase going from point A to point B. One of the conveniences of the distribution system is most often the distribution feeders are radial. What that means is if you start from your substation or your subtransmission point, there is basically a branching path, just like a tree, down to your end-use load. There's no loops or mesh or anything like that typically. There are mesh distribution systems, and I'll make some caveats here later about which solvers inside GridLAB-D can handle mesh systems and which can't. But for the most part, at least in the United States, and I would imagine it's fairly similar in other parts of the world, distribution systems are pretty much a radial system. You have one source point and everything kind of branches out from there. The other thing to keep in mind is on the distribution system, your impedance values, so your resistance and your inductance, are typically a lot higher, and that's just the nature of the cables. You're not doing any of the things they do on transmission, like the transposition of the lines to help cancel out the magnetic effects, things of that nature. So your impedance values end up a little higher, so overall your losses are probably a little bit more than you expect out of a transmission system. So I've thrown around the term balanced and unbalanced, and what exactly does that mean? So if we look at these two different phasor diagrams here, if you look at the first one, it says the voltage source is balanced, and I don't know if the picture shows it very well, but if you look at the right-hand side, you have 1 volt at 0 degrees, and then the A, B, and C voltages are all 120 degrees out of phase with each other. So if you were going to draw, it looks weird, I can't tell if it's actually equilateral, but each one of these triangles should be 120 degrees between them. Whereas if you go down to the unbalanced, you can have both differing magnitudes. So if you look at the A, B, and C, one has a 1 volt, one has a 0.97, one has a 1.03, and they also may not necessarily be 120 degrees out of phase. Like the A and B are 120 degrees, but the next one is actually 123 degrees. So there's no guarantee that everything will balance out into a nice equal system. And one of the consequences of that is you won't be able to collapse it down to the positive sequence component. So in terms of distribution system equipment, there's a variety of different things that are in both the transmission system and the distribution system. But from the GridLAB-D perspective, this is a list of most of the things we deal with on a regular basis for the distribution system modeling. Overhead lines, underground lines, just your normal distribution lines, either full three-phase or single-phase or two-phase laterals. Transformers to step down your voltage between your subtransmission and your other networks. Voltage regulators or load tap changers, if you want to call them that. Basically, it's a variable tap transformer that adjusts automatically to keep your voltage within a certain range. Then things like shunt capacitors, if you have voltage or reactive power issues, including those in your system model. There are a bunch of other things that we're not going to go into a whole lot of detail here, like switches, reclosers, and fuses. Those are more in the reliability module. And then there's also lightning protection, which we don't model at this point inside GridLAB-D, so we won't get into too much depth on there. But that is a component of the distribution system that you'll often see in a substation or on special circumstances of getting power from point A to point B down there. So just a picture of a transmission tower. Fairly simple tower here. This one has two parallel sets of lines on it. You always have all three of them. And this particular tower, nothing special about it. You don't see the grounding wires on the top or anything like that. Distribution system, obviously smaller wires. There's fewer insulators your insulators are smaller, so obviously it's lower voltage. Typically, all on the pole top. The spacing is very important, which we'll get into a little bit later. And this one happens to show all three phases, but that's not a requirement. You may only have the first two phases here or just a single phase, especially on some of your rural feeders. If there's just a single phase lateral going out, say 20 miles to serve the one rancher or farmer that happens to be out that distance. So system representations, there's two different ways to kind of look at power flow. One of these is known as positive sequence, and basically what that is under the assumption that the system is balanced, you can collapse it down into a single phase equivalent. So instead of having to solve the A, B, and C phases explicitly, you basically just solve the entire model off of the A phase. This is used quite a bit in transmission systems, and it's a fairly valid assumption on that end of things, just because the system is operated fairly balanced. They do things like the line transposition and have their transformers in there appropriately to make sure the system is pretty much sending the same amount of current on phase A, B, and C of your power system. Positive sequence, I should note, is just one portion of what's known as the sequential components. So theoretically, you can do an unbalanced power flow with the positive sequence, and then there's also the negative sequence and zero sequence, but we don't do that inside GridLAB-D. We actually explicitly model them as the full three-phase, which is what we're getting into on the right-hand column here. So rather than just having a single-phase equivalent, we're actually explicitly modeling all three phases on the power system and the neutral where appropriate. The big thing that's important there is if you think about your traditional transmission level power flow, a lot of times your line impedance is just a single complex number. You'll have a real and a reactive portion to it. Whereas on the distribution system, you'll have basically 9 complex numbers. So you'll have the 3 complex numbers associated with your individual A, B, and C phase, and then you have the mutual inductances between the different phases. And that gets into the electromagnetic coupling between the lines. This is especially important on the distribution system since you're not assuming transposition every 30 miles or so like you do on the transmission system, and you're assuming that those magnetic effects aren't being canceled out just by swapping positions of the lines every so often. So what this allows us to do by explicitly modeling all 3 phases is we can model a lot more of the systems that are present on a distribution system in greater detail. This includes single-phase loads, 2-phase loads, and what we call split-phase systems. Split-phase systems are also known as like single-phase center-tapped. This is what we use in the United States for our distribution network. It's basically where you get the plus or minus 120 and the 240 across the 2. And there will be an example of that later in the presentation. So just kind of a comparison of the model. I mentioned how a typical transmission line is done with just a single complex number for an impedance, and that's what we have here on the left-hand side, the positive sequence model. So you'll have your voltage on the from side, your voltage on the to side, and then just a single impedance and the current that flows through that line. Whereas if you do the full unbalanced, you'll actually have the impedance associated with each individual line, so your A, B, and C, and then your neutral if appropriate, and then you'll have any of the magnetic coupling between them as well. And that's handled by this AB, AC, BA, BC, and so on terms inside your 3x3 matrix. So instead of it being just kind of a nice little simple equation, it actually enters into the realm of matrix equations. So not terribly complicated. It's still the same basic idea. It's all based off of fundamental circuits. It's just you're handling a lot more elements, and it's a little more accurate in terms of your modeling and a little more complex to solve. But the fundamental concepts are still the same. You've just added more components. So three-phase unbalance, I pointed out that matrix before. The way we get to it inside GridLAB-D is you start with your physical system, and then you parameterize those values. So basically, what's the spacing of the lines on the pole top and how far they are from the ground. And then if you use a variety of different equations, including Carson's equations and Carson's reductions. And if you look in William Kirsting's book, I think it's Distribution Power System Analysis, I believe is the title, it'll have all of these equations in there. And it's basically using those distances and the size of your conductors and everything like that, you can convert this physical system down into a matrix representation for your model. And that'll give you the impedance over whatever distance the line is, and then also factor in all those mutual impedances and mutual effects on the system. So if we take a look at one of the GridLAB-D objects to do the overhead line code, this particular one is showing you what we call a BCN overhead line. So it only has a BC and neutral phase modeled on it, so there is no phase A. And you guys got into this a little bit in the first module, but basically the name of the object, just so you can identify it in any of your outputs. And then the from and to will dictate how it's connected to your system. So this particular one goes from a bus called node 632 and then goes to another bus called node 645. It happens to be 500 feet in length, and it uses this particular line configuration, which is shown on the right-hand side. So this configuration code is where you get a lot of the physical parameters of the system lined up. If we look at the representation down here, this would be equivalent to that tower we just saw here, only basically that middle phase is missing. So if you look at the configuration, it'll have the conductors that are making up the individual wires of the system, and then the overall line spacing, which is their physical distance in space. So the conductor information has just some generic information you would expect for a piece of wire in the air. Basically how big it is and how much resistance per mile there is. If you get into the line spacing, that tells you the physical layout again. So it'll tell you the distance between phase B and C is 7 feet, but the difference between C and the neutral is 5.657, and B and the neutral is 5 feet. So this neutral is probably actually supposed to be on the other side of this line. But you can include that information, and if you want to include the ground capacitance effects, you would have to also have your distance between your neutral and ground. But that's just kind of a quick overview of how something like an overhead line would be modeled inside GridLAB-D. So underground cables, just to get into a little more detail on how they're actually situated, a lot of times you'll have your power and ground in the same package, for lack of better terms. So this is just a single phase conductor. The center part here is the actual power conductor, for lack of better terms. So this would be your A, B, or C phase. And then a lot of times your underground cables have the grounding, or sometimes even the neutral, if it's done as a particular method, as strands along the outside. So it's basically the shielding on the system to help keep the EMI down and all of those fun things. But when you model this in GridLab, which we'll get into next, I couldn't remember if that was the next slide or not, basically you'll see that the underground line conductor information is a little more complex than it was for the overhead line. Obviously because you have those neutral conductors in there, which are down here, the neutral GMR, which is the geometric mean radius, if I remember correctly. Neutral resistance, neutral diameter, the number of strands, so if there's 6 or if you have 20 of them, that'll depend on your individual cable. And then if there's any shielding, you can include the shielding resistance and then the geometric mean radius on those as well. If I remember correctly, the shield GMR and resistance only comes into effect if you want to factor in the capacitance of the system, but I'd have to go look that up for sure. But other than the conductor specification, you see the line spacing is done very similar to how it was on the overhead line, and the actual line configuration looks pretty much identical. And then when you specify the line itself, you have object underground line instead of object overhead line, but everything else is pretty much identical to how it was before. And that's very common of all of the what we refer to as branch types inside GridLAB-D. Overhead lines, underground lines, transformers, anything that will go between buses or nodes is considered a branch inside GridLAB, and it'll follow a very similar structure to this, where it'll have basically a from node, a to node, and then some form of configuration. So if we get into transformers, obviously when you're in your distribution system, you're going to have to somehow get from the transmission voltage down to your end-use load voltage and any intermediate voltages in between there. You have your typical pole mount transformer here on the left, and then a pad mount transformer over here on the right. And the code for those, well, this is actually a good point to interject this. Earlier I mentioned the split-phase center tap or the single-phase center tap. This is basically the model for distribution system transformers in the United States. This is the final, I believe it's called the service transformer, where you're going from your distribution voltage down to your end-use load voltage. So this X1 and X2 would typically be connected between either two of your phases, either A and B, or B and C, or C and A, or more commonly between like A and ground, or A and neutral, B and neutral, something like that. And then on the end-use side, you actually get this L1, N, and L2. So your N is still your neutral, but the way it's basically wound on the system, instead of just getting a single step down, you're actually you're stepping down your voltage and then also splitting it into two different components. And that's where you get the or the 120 L1, the 120 L2, and then across the two legs, you'll get your 240 volts, which is the common distribution voltage inside the United States. European models typically don't have this plus or minus 120, they just do the 240 directly, and a lot of them actually do the three-phase directly to the home instead of the split-phase model. But you can model all that in GridLAB-D. It's just a little different. We're obviously predominantly focused on the North American system, since that's where we do all of our research, but you can model the three-phase components like the European components inside without any issues. So if we look at how a transformer is actually written up inside GridLAB-D, if you notice on the left, it again looks very, very similar to how the other branch items were. You'll have your name of the item, the connection points, so the from and to buses or nodes, the phases of it, and then these extra things on here, this group ID. I don't know if you guys got into that last time or not. It's basically a way of grouping objects together. So if you want to use something like a collector or some of the reliability components, the group ID is a nice way to say, okay, every single transformer that goes between like a node and a house, call it distribution transformer. So if I want to look at the statistics on those, or if I want to create a particular set of faults on those, I don't have to go in and individually find them all. This nominal voltage term, I think, might actually be an error. I don't believe that needs to be in here for the transformer. I don't even think it's a published property, so this will probably actually error if you try to run this. Configuration code, and this is the actual information about the transformer itself. So the important things you see are the primary voltage and the secondary voltage, and that's basically defining your taps ratio. And then you have your power ratings, and that's in combination with your taps ratio, and then your impedance values, which are given in per unit, will give you the actual impedance on the system. It's kind of a side note, but it's important if you want to add other things into GridLAB-D. One of the other fundamental differences between GridLAB-D's distribution solver and a lot of transmission solvers is a lot of your transmission solvers are typically done in per unit. So everything is normalized against a common system base or a common system voltage, and you'll see values like 1 or 0.95 or anything like that. GridLAB-D solves everything in the actual values, so rather than using the per unit transform, we actually go in and we explicitly model the impedance and the turns ratios on the transformer, and everything is solved in the full voltage range. So you'll get answers that'll say like 7200 at angle 0, 7295 at angle 0, things like that. And then on the secondary side, you'll get 120. You won't get 1.0 per unit and 1.0 per unit on both sides of it. You can, of course, convert everything to per unit if you want, but by default, GridLAB-D in its output will just give you the the actual rated value, or the actual physical values of the voltage and current. If you want to do any per unit representation, you have to do it either through like a MATLAB or an Excel script or something like that. So voltage regulators, on a fundamental level, they're basically just special transformers. And what they allow it to do is they allow the distribution system to adjust the voltage in order to compensate for loading or voltage drops. And this can be both from the load side and from the transmission side. So if your transmission voltage fluctuates a little bit, obviously that's going to impact your distribution voltage. So voltage regulators or load tap changers will have the ability to adjust up or down in order to compensate for transmission system variations. The other place they're commonly used is if you have a very different power consumption on your feeder, especially during like the nighttime hours or the daytime hours. So if you have a heavier load, if you go back to just Ohm's law, you'll be pushing more current through your line, so whatever your impedance is, you're going to get a greater voltage drop on there. So you have to compensate for that in order to make sure you aren't violating any of the ANSI voltage standards or whatever particular voltage standard applies where you're modeling your system. But as mentioned, voltage regulators, they're basically just special transformers. They are typically automatic, but it's a variable tap ratio transformer. And just kind of a simple representation of it here. If you notice, the left-hand side looks very much like the other transformers, and the difference is instead of there just being a secondary coil over here, you're actually pulling taps off of the primary coil in different spots. And just a quick note down here, which is also listed on the slide, voltage regulators are represented as ideal, so it's basically an auto transformer, even though this shows Z series and Z shunt. We don't really factor in the losses inside GridLAB-D. They could be added, but at present we haven't really had a need to model those particular losses. We've been interested more in the secondary transformer losses. So if you look at the voltage regulator code, on the left-hand side, again, it's another branch object, so it looks pretty much identical to everything else we've seen so far. You have your name, the phases that it's actually connected to, the connection points, and in this configuration telling you what that voltage regulator actually represents. And the regulator configuration is only a single object, just like the transformers. It's not multiple objects like the line configurations. But you can see there's a lot of different settings inside here, and a lot of these are dictated by what particular mode of operation you want to put the regulator in. If you want to do it in what we call either manual control or output voltage, line drop compensation, or a remote sensing node. So obviously if you put it in line drop compensation, all of these compensator settings will be valid, but if you're not, then those pretty much won't do anything. The important ones for pretty much every mode of operation are, of course, your raised taps, your lower taps, your band center, bandwidth, and I think the regulation term down here. A lot of the other ones, they're in there for specific modes of operation, or they're extra information to help kind of refine your model a little further. One example of that is this time delay setting up here. That is basically the lockout. Well, I guess that one's not the lockout delay, but it's a delay between when tap changes can occur on your system. So when you're doing time series simulations, if you set this to 0, you'll be able to get instantaneous changes on your system. So you could go all the way from basically tap 0 to tap 15 instantaneously. Whereas if you want to get a more realistic behavior of how the system is progressing over time, if you set this to like 30 seconds, it'll only allow one tap change every 30 seconds, and you'll see how the voltage evolves over time for whatever system you're studying. So shunt capacitors, as I mentioned before, those are used a lot for voltage control or some form of reactive power control, and they have a variety of different operation modes. You'll notice the overall structure looks a little different. The capacitor is the first object we get to that is what we call a node or a bus. Basically everything inside the GridLAB-D Powerflow module breaks down into either a link object or a branch object, or it gets down into a node or a bus object. And inside GridLab itself, they're just called links and nodes. Capacitor is just done as a node itself, so it's only a single point connection on the system. There's no from and to. So you just give it basically the phases, the name, and then all of this other information is related to the capacitor itself. So some obvious things like what is the size of the capacitor, and that'll determine how it affects your system. And then the different control methods will have their different parameters as well. As it's listed here, we have manual, volt, VAR, VAR volt, and current. So manual control is basically either via a player or some other control method. You're telling when the switches on the capacitor banks to open and close. Voltage is if you wanted to maintain a particular voltage set point and specify some deadbands, it'll switch the capacitors in and off in accordance with that. VAR and VAR volt, well, VAR and current actually are very similar. They are more for reactive power compensation. So if you want to switch in a capacitor bank to help reduce the inductive draw on a system, you can specify which link they want to look at and then specify the set points, and they'll switch in and out. VAR volt is kind of a combination of the two. You can basically specify a voltage band and a reactive power band for it to operate in. And I can't remember what the preference is there. It'll do one before the other. I think it maintains voltage before VARs, but I'm not positive. I'd have to look at the documentation. But just some of the other parameters that influence some of these modules is not modules, but the capacitor itself. PT phase is which phases to monitor. So that's basically what phase your potential transformer is on, or in the case of the volt VAR or the VAR, whichever phase on the link object you want to monitor the reactive power out of. Nominal value determines the impedance value, or nominal voltage. This value is also required for all node objects in general. It's used by the capacitor to help determine the nominal impedance. It basically takes your ideal reactive power and then converts it using the voltage into an impedance value. Nominal voltage itself is used by Powerflow to determine kind of a starting point for all of your nodes on your system, and it's also to make sure that you don't inadvertently connect two different voltage points without a transformer. Control level, just another variation on how you operate the capacitor, whether or not each one of these individual phases can switch by themselves, or if it's an all or nothing type deal. And then the lockout time is very similar to the time delay on the regulator. Basically, it'll prevent your capacitor from switching too many times. And then remote sense B, they're used for looking at other points on the system, and that's all covered in the documentation. Basically, remote sense is just if you ever want to look at a particular line for VAR or current VAR or current mode, or if you want to operate it in volt mode, you can tell it remote sense and have your capacitor switch off of, say, an end-of-line voltage instead of wherever it's actually attached.
So something I want to point out there real quick. This is part of one of the interesting things that you can do with GridLAB because of the time-varying nature of the controls that are built into it. So that's some of the more traditional tools, some of the more classic tools don't capture those kind of time-varying control features. So, for example, with those controls in the regulator and the capacitor, it's actually quite easy to set up an oscillator inside of GridLAB-D where you can have the controls fighting each other. So it's a little bit because of the time series nature of it, you can kind of experiment with some of those controls. You can look at a combination of traditional and non-traditional controls and make sure that you understand how all the timing of those controls work together.
Yep, no, those are very good points, and a lot of those things, they don't make sense from a traditional static power flow point of view, but as Jason mentioned, when you start getting into the time evolution of things and you're doing more of your weekly, monthly, or yearly simulations, you'll get into cases where your controls will fight each other, and that's one way of preventing it, or one way of better modeling it, so if you are interested in how your controls are going to interact, you can capture that explicit behavior. So the other aspect of distribution system modeling that we've obviously missed so far is the end-use load modeling. So we've had basically the links getting from point A to point B, but the big thing on a distribution system is what is the load on the system, and that's what's referred to as the end-use. So the primary purpose is, of course, to supply power from your transmission system or your sub-transmission system down to your end-use loads. You got to get power to your house so you can run your toaster, your TV, anything like that. And inside GridLAB-D, you can represent your objects in a variety of different manners. Basically, there's 4 different types. You can do what's known as a time invariant load model or a Zipp model, and that's constant impedance, constant current, and constant power model. We'll get into that more here in just a second. Those are your traditional like transmission level models where you just specify the power, impedance, and current of a particular point on the system, and it's the same for all time. It never changes, always the exact same value, and then the power flow adjusts accordingly. You can also do a time variant load model, which is basically the same thing as the time invariant, only you're somehow adjusting those zip fractions or those zip components with time, either via a player or a schedule, or if you have a specific object that's influencing those in relation to some form of behavior it's modeling. And that kind of transitions into what we call physical load models, and that's where you're actually modeling the system in a lot more accurate detail related to some physical device. So if you had a motor, you may define a particular zip fraction, and then the constant impedance value might be related to the resistance inside the windings on your motor or something similar. Very closely related to that is what we call our multi-state physical load models. And this is basically, you're still using those zip fractions, but the zip fraction will change not only with time, but with also the state the system is in. And we'll get into it here in a second, but the best example of that is like a heating, ventilating, and air conditioning system, an HVAC system. So if your air conditioning is off, obviously it's not going to be really drawing any power. If the air conditioning is on, you're going to have the blower motor and the compressor running, and that'll be a particular zip fraction. However, a lot of times when that compressor kicks off, the fan will still run, or the fan blower will still run for a little while, so then you'll have that aspect of the multi-state running and that particular zip fraction. So it'll vary based off of what the state is on the system and kind of what the temperature is in the house. And that's just one example, but it's the best example of a multi-state physical load.
So Frank, there's a question on the chat line there. Question is, can loads be aggregated to the node level, i.e. can you specify P and Q demand at each of the nodes rather than at the single customer level?
To a degree. You can specify what's just known as like an object load, and that's basically the equivalent of a node, and specify the explicit power or real and reactive power at that point. You can also do what we call the parent-child relationship, where you include the individual customer loads down below, and then it automatically aggregates it up to the connecting node. So if you put like a meter there, you could figure it out. In terms of doing it in kind of an automagic way, so if you just put in a whole bunch of different load demands and you wanted it to consolidate down into a single point, you would have to do that with something like a runtime class. I'm not sure if I've fully answered that question, but basically the idea is you can do the individual loads, but if you have an aggregation available to you, you don't have to go down and model every individual house. You can say this particular object load actually represents 10 houses, and here's how the load changes with time.
Right. Yeah, I think basically you can do, effectively you can do load shapes, so you can play back in shapes in there with P's and Q's. You can adjust zip fractions. They can be time varying or not time varying.
Yep.
And I think what Frank's got over the next few slides, we'll kind of go into that a little bit more. Definitely let's revisit this at the end of the next few slides if there's still more questions.
Yep. Yeah, and a lot of this will come down to specific applications as well. There's different ways of approaching how you want to change either your aggregate load or what you mean by your aggregate load. But if we get into the first model here, the time invariant load models, and again, these are used for kind of static single solution power flow calculations, or it's used for a model that doesn't really change with time. I guess the best example of that is the capacitors we just went over. The capacitor is a fixed impedance, no matter how you look at it. You'll specify it as a particular reactive power, but at the end of the day, it is just basically a large capacitor on the system, so that impedance will adjust the impedance will be fixed, but the reactive power it's consuming will be based off of the voltage and other system conditions. So these are generally used for capacity planning or peak load, or as I mentioned, just a load that doesn't have any variation. It's always there. I can't think of a really compelling example beyond a capacitor, but it would just be a load that you either don't care what the different states are, or it never changes enough to actually model it in anything more complex. And this is just the traditional Zipp Load model. which if we look at the representation here, basically you have your voltage source, and then your load is composed of the constant impedance, the constant current, and the constant power fraction. And these all get aggregated up into the overall power, both real and reactive, that your system is consuming through this wonderfully long equation here, which is just taking in your different percentages, what portion of the load fraction is an impedance, a current, or power, and then applying basically the power factor to those and adding them all together. So of course your total load on the system is a combination of the constant impedance portion, the constant current portion, and constant power portion, and obviously you can't have more than 100%, so all of those numbers do have to add up to 1. But it's a fairly simple load model, but pretty much any follow-on load model, even if it's a load state, is built on top of this. Even if it's changing these zip fractions or these zip components with time, it is still basically built off of this same zip model. So a couple of years ago, we actually did some lab studies where we plugged in a bunch of different devices and put a power quality meter on them, basically, and looked at how the different zip fractions were affected and what they represented, so we could get a little better end-use model out of these. And it's important to caveat all this with, this was basically a least squares fit to get the fractions to fit the measured data we have. So when you look at some of these values, they may not quite make sense, but this is the model representation. So if we look at kind of the real and reactive power for a 13-watt compact fluorescent light bulb, you see the impedance portion was roughly 40%. There was a very small constant current portion, and most of it was constant power, presumably because of the electronics inside it to actually do the ballast and all the fun stuff associated with getting the fluorescent light to write. And then, of course, your different power factors, so 0.88, 0.78, and negative for lagging, I believe, and then positive for leading. So if we want to get into a little bit more complex load, you can get into time-variant load models. And this is kind of alluding to what Jason was talking about earlier with load shapes or load profiles. Basically, you can either fix portions of your model or none of the model at all, and you'll change those zip fractions and those zip coefficients with some time-varying function. Either you'll have like a player or a schedule or a load shape on them, or you'll have something that is driving how those different fractions change with time. And basically that's to get like your aggregate load model that was discussed earlier. If you wanted to play in a data file of measured like SCADA data or something similar to that, you could apply that to just an object load and play that value in as a constant power, but it's a time-varying power, and that'll give you an accurate representation of what your load was doing without going down into all the depth of the 2,000 houses that are attached below it. So that might actually be a better answer to the question that was posed earlier. But a lot of times this is just a nice way to do kind of quick studies, or if you have the aggregate or some form of source data available, rather than going in and explicitly modeling all of your end-use devices, if you have a particular measurement point on the system, you'll just play that in to your GridLAB-D model and not worry about the underlying detail. So if we look at like an example load profile, this is just showing the load in kilowatts with time. So instead of just having this initial value for all time for your model, which you might have with a lot of traditional transmission system models, you're actually changing it with time. So this could be something like, this is an early morning peak associated with people getting up, cooking their breakfast, getting ready for work. Then everybody goes to work around here, so it drops down because they're all on the road. Then, of course, you get your normal peak when either your heating load picks up or your air conditioning load, or if this was some type of industrial process, maybe this is some type of pre-start, and then this is the actual consumption throughout the day. Basically, it gives you a lot of flexibility to model either different types of aggregation or even different types of specific loads if there's an explicit behavior you're trying to capture in the system. So if you know, like if this was an industrial process, that you have meters on a steel plant and this is how the load looks throughout the day, you could play that in directly and figure out what its impacts are in the distribution system real easily. So the Zipp Load itself, if we just do the straight up simple form of it, you basically have this object Zipp Load. The group ID, again, is just kind of an extra thing in there for grouping objects. We'll get into that probably in a later module, I would assume. Excuse me. And then you just specify all of your different fractions. So you specify the base power, which is kind of the overall power the system is going to consume. and then your power fraction, your impedance fraction, your current fraction, and then the power factor associated with each of those. And with more or less those 7 pieces of information, you'll have everything you need to solve for those explicit constant current, constant impedance, and constant power portions of the Zipp model. But in this particular case, you're actually changing it with time. And this is a really good example for doing like an aggregate load. We call it plug load, so this could be basically all of the end-use appliances inside a house, but you could easily make this something else. But what you're basically doing is we're varying the overall power the system consumes by this plug 1 times a particular scaling constant. And this plug 1 is actually the schedule over here, and I don't know if you guys are familiar with this formatting. It's a little odd. I believe it's modeled off of the Unix cron format, if I remember correctly. But let's see if I even remember. I think this is minutes, and I think this is hours. So basically, for like the first 23 minutes of the day, you're going to have a baseline consumption of 0.1605, and then for the 24 through 59 minute of that first hour, it's going to be 0.1381. These individual values for whatever time of day it is will get multiplied by this 2.828958. And then, of course, all of the different fractions will dictate how that gets translated into your individual components. So this particular load, you can see, is it kind of dips down below here and then rises and has a little bit of variation and then goes up higher around the 5 o'clock. So it might actually be very similar to this load shape we see here, but it just provides a way of doing the time-varying nature of the load itself. And in this particular case, we're only adjusting the overall power consumption. We're leaving all the fractions and all of the power factors the same, but you could actually either change the schedule so it applied directly to the power fraction or the impedance fraction, or you could even put multiple schedules on here and vary each one of these with time. So you could basically have 7 different schedules and change your load completely throughout all portions of the day. So the next step of that is just kind of adding a layer of complexity, and that's looking at the physical load models. So these load models, rather than being like a measurement point or kind of an aggregation of the system, it's more based off the actual physical model of the system. So HVAC is listed here, but that actually is a better example for the next one, the multi-state physical load models. But things like energy storage, even something like a motor, you could argue, could go under here. So if you know any of the actual components or the component quantities of a physical device, this would be how you would plug those in. And that CFL example earlier actually fits really well into this, where if through some form of measurement you know exactly what the Zipp fractions and the Zipp components are, you can plug those in, and that Zipp load now becomes a physical representation of a compact fluorescent light bulb. It may not be useful to model a 13-watt compact fluorescent light bulb in your system, but depending on what you're looking at, you may want that level of detail. So it allows you to go down to the explicit individual device if you need it, or if you have some larger device, maybe if you have water pumping or something similar on your system, and it's running constantly, maybe it's a gas compression turbine or something similar to that, then you'll know the explicit fractions of that model and just plug them in, and instead of having to deal with the intricacies of whatever the gas turbine's doing, you just say, okay, this particular load is a gas turbine. Or a gas compression turbine. I'm sorry, it's not really a gas turbine. But you could do that, just to kind of interject that here. If you wanted to do some form of time-varying generation, you can apply those in the same fashion. You're basically just applying a negative load. It's kind of weird to think about, and we'll probably get into that more when we get into the generators module, but it's just something to throw out there for now. So the next way to look at it is if you have a kind of a physical model for your system, and then you also have multiple states. And this will get into in a whole lot more detail inside the residential module, but this is basically you can think of it as like an equivalent circuit for your average residential house. So the air temperature and the mass temperature and all of the different sources of heat and influences on the system in terms of how is the heat being lost, how is the heat being gained. And this is basically what's used to determine the current air temperature in the home for affecting the HVAC system. So based off of that model, you'll have a bunch of different states to your system. Obviously, the HVAC system isn't running all the time. Sometimes it's off, sometimes just the blowers running, things of that nature. And where this is really nice is you'll have your Zipp model varying with different states of the system, but different conditions going into the system will be updated, and you'll be able to track the behavior as necessary. One of the classic examples of that is actually on this slide here. If you're doing something like a conservation voltage reduction study, if you had, say, electric heating, for a very simple example, your heat produced into the system, of course, is dictated by Ohm's law. So as you reduce the voltage, the power going through your resistor is going to go down. So in order to still heat the air in your house by the same amount you wanted to, it's going to take a little while longer. And that's kind of what's shown here on the right. I don't know if this was exactly a heating example, but basically with the lower voltage here, the 118 volts, you see it takes a lot longer before the HVAC system actually turns off. And that, if it was a heating load, could be associated with you're not producing as much heat into the house, and it's going to take longer for it to fill in. This is really nice, especially for doing different types of mitigation strategies, demand response, things of that nature. The fact that the physical multi-state model is still behaving how an actual system was, but it's factoring in all the system-level effects that you're trying to influence and see what kind of benefits you can get. So it's nice that it captures that level of detail, especially for the distribution system analysis where, you know, you may want to reduce the voltage by 2 volts, but what does that actually get you? It's not just a straight one-for-one trade there of, okay, I got 2 volts reduction, so the power must go down by that. There's a lot of the secondary effects that these physical load models will help capture, and this is the best example of that, is by reducing that voltage, it's not turning off at the same point. The house still has to meet its internal conditions, so you're getting kind of an unexpected benefit, I guess, or an unexpected impact on the system. So that's where these multi-state models really come in into play a lot more in your system-level studies. Is your individual devices still maintain their behavior, and then when they interact with the power flow, obviously the system's going to change with time.
There was a good question on the chat session there that I wanted to kind of follow up on. So every one of these models is based off of a Zipp model itself. So there's Zipp fractions, and there's a certain P and Q that are being delivered to the power system. And so when PowerFlow solves these solutions at any given moment, it is using that Zipp fraction and that, I'll call it base power load that's coming out of it. What these other models do, these kind of, Frank's calling them the physical load models and some of the control models and things like that, they are capturing how those things affect certain physical properties within the system. The house is a good example. The other one I like to use a lot is a hot water heater. So a hot water heater is a resistive coil, so its Zipp fraction is literally 100. It's all impedance. Now that fraction stays the same over time, but if you lower the voltage, then what happens is you get less BTUs getting put into the water. So if you don't capture that kind of closed-loop control cycle that goes on with the thermal effects inside that device, then you will miss the effects of how that transforms over time. So the kind of classic example is CVR with or volt bar optimization with hot water heaters. If you lower the voltage, yes, instantaneously you will lower the power consumption on the feeder. However, you do not lower the energy consumption because it still takes the same number of BTUs to basically heat up that water and get you to the heat level that you want coming out of the temperature level that you want coming out of that hot water heater. But in the end, everything is modeled as a Zipp fraction. In fact, I think in most of the PowerFlow methods we do, those almost invariably get converted into current injections. So you could even look at it that way, is that all the loads in the end finally get just put in as current injections into the model. But really, they all support Zipp model on the non-time varying portion of the solution. So at any instantaneous solution, it's using a Zipp model. All of these kind of more advanced pieces come as a function of time.
Yep, very true. And I will caveat that with, even though they all do get reduced down to a current injection, that current injection is being updated on each pass of the PowerFlow solver. So the particular current injection isn't fixed to whatever your entering voltage was. It'll actually adjust with whatever the iterative solution voltage is as well. And we'll get into that a little bit more here later in the presentation when we get into the different solver methods. So the multi-state physical models, just kind of a little more detail. Obviously, HVAC system, so you have off, cooling, heating, and then auxiliary heating. So just different particular states of your system and how those zip fractions are going to change with whatever condition your system is in. And obviously, there might be a time behavior associated with this. Either you're trying to reach a set point, or maybe it's some type of scheduled behavior of every morning at 6 o'clock this particular device turns on and goes into this mode, and then it goes and turns off, or something similar to that. So it's basically just adding that level of detail onto your extremely simple zip model and how it's going to change with time or particular condition on your system. Just giving you a more accurate representation of your end-use loads. And this is just kind of a state diagram of the HVAC system in particular. So obviously, there's going to be some type of behavior modeled in those different states of how can you get between state 1 and state 2. Obviously, going between cooling and emergency heating is not a direct path. It has to go through other things. So this is just kind of a quick example, but you can see how pretty much any physical load model you could conceivably reduce it down into either a 4-state or even a 16-state or anything like that type diagram, and then just model how these transitions are and just basically have a zip fraction associated with each one of these states. So just another example here, more explicitly on the HVAC multiple states. The states are actually this diagram down here. I believe 1 is off, 2 is cooling, 3 is heating, and then 4 is emergency. Somebody's inviting me to a conference call. Basically, if we look at the apparent power through all of this, you'll notice it looks very similar to the states. That's just by coincidence here. So you have your apparent power and then the outside temperature. So as the outside temperature varies throughout the day, you'll notice the duty cycle on this apparent power changes, and I'm going to get rid of that. I don't know if you guys could hear it ringing, so it might have been annoying to you as well. Basically, the HVAC apparent power is going to be affected by this outside temperature, and that's basically just by these states. So if you look, this particular system is in heating quite a bit of the time, but when the temperature drops a bit, you're going into that emergency heating a lot more. And this is just another way of highlighting kind of the agent-based behavior of GridLAB-D. You see that even though the outside temperature is starting to go up here, you're in that emergency heating portion for a lot longer just because of how cold the temperature did get, or maybe, well, actually over here I think there was a set point change. But basically you're doing that explicit house and how the set point and the air temperature is changing inside there, reflecting that onto the Powerflow module and how the individual zip components are changing, and that's affecting your overall apparent power on that particular house. Then if you turn around and aggregate this up to 1,000 homes on your system, you'll get the overall distribution system impacts and be able to study if you want to look at a particular demand response, maybe you're doing temperature set point changes, or if you wanted to do some type of incentive program, something of that nature. But basically you'll take each of these individual little homes and they'll add their particular piece onto the Powerflow solver. It'll solve the entire system, and you can look at whatever particular metric you want to examine. This is actually a good place to kind of pause for a second. Does anybody need like a 5 or 10 minute break or anything, or should we just keep plowing through?
Peter, yeah, that's a good question. So the question is, every state transition would trigger a Powerflow calculation. How does this scale from a computational point of view if one has 100,000 houses? Very badly. That's an issue we've run into, and we've gotten a couple workarounds that we've used to kind of, I don't know, sidestep that problem. They're not the best solutions. So for example, right now we use what we call like a minimum time step, where we basically say, and you'll see these a lot in some of our studies. Basically, we can set a global variable that's called minimum time step, and we'll set it to say like 60 seconds. And what that does is it basically decouples the solution for 60 seconds. All of the individual objects still update their own internal states, but they don't check with everybody else to see if they need to update the information shared across the objects. So it does introduce a certain level of uncertainty into the problem, and so if it's kind of a trade-off of speed versus accuracy. We found that at about a 1 minute time step using load models plus residential models plus all these kind of other things that we're using quite a bit, that 1 minute seems to be a fairly, you don't really see much of an error, something on the order of like maybe 0.5% to 1% error of your energy consumption over the entire annual simulation. But you also speed it up by 60 to 120 times. So it's a bit of a trade-off there. Some of the other studies, for example, if you want to start looking at maybe say like solar transients, when you want to look at cloud passage over a solar panel, and you want to focus down on like a 45-second window that's really tight, then that's when we'll make our minimum time step something like a second, and we'll make sure that all these devices are actually sharing their information at 1 second intervals rather than 1 minute intervals. So that's one way that we've gotten around it. The more ideal way would be that you could effectively set a convergence criteria between all the different devices, basically define the boundaries between all the different agents and say, okay, unless I see a value of XYZ change more than 1%, then I don't want to update my state from it. It's a route we haven't gone so far. I would call our approach at this point the brute force approach. So there's definitely some work that could go into that and probably speed that up. Now, as far as size, when we're using these 1 minute time steps, I've created models that have about 100,000 houses. That's about the limit that I've tried it up to. And when you use that 1 minute time step, it does not seem to slow down the simulation too much. But when you do not use the 1 minute time step, it slows down significantly, and it can become a very computational intensive. So I didn't see any hands raised to take a break. So,
can I raise my hand? So we'll take like a 5-minute break here. If nobody else wants one, I just need to quick refill my cup here.
So yeah, let's try. We'll take a break until about 9:15 here, and then we'll get started again.
Okay.
Feel free. I will be sitting here still, so if there's any chat questions, feel free to shoot them across. Sorry, yeah, everyone can go ahead and stay on the line. We'll just, I just got it muted here. In fact, what I'll do is I'll leave the phone line on, and so if you just hang on, we'll be right back here in just a minute. So during these break times, I'm going to go ahead and unmute everybody's phones. So, so if there's any conversations that want to go on, go right ahead. But just be aware that if there's a lot of background noise, I'll have to mute everyone again. Aaron, as far as the aggregated value, the best way to go about that is to use a load object if you're doing aggregation like that. The load objects are pretty generic. They have all the capabilities that the Zipp Load object has that Frank showed a few minutes ago. So you can put in your zip fractions, you can put in a base power, you can directly feed in P and Q if you want. So they're very flexible. What we'll do at the end here is we'll go through and I'll walk through a couple of examples just using a load object. And usually the way we'll set that up is we will create a load object that is childed to a meter. And we'll use that so we can use that meter as a way of doing like energy measurements over the course of, say, a month. We want to know how much energy is consumed by that load. The meter objects allow us to do those measurements on that. So yeah, we can walk through a quick example of that when we get to the end here. But I would definitely say load object is your best bet.
All right, well, it looks like we're back at 9:15, so, well, at least 9:15 local time here. So time to get going again. Hopefully any questions you guys had right away were answered. If not, we'll again have time at the end of this to discuss any of the specific ones you may have. If we get into kind of the more detail of how the Powerflow solver inside GridLAB-D works, it's predominantly composed of two different methods of finding the solution to the Powerflow. We use what's known as the forward-backward sweep method and the Newton-Raphson current injection method. And there's just kind of some quick information on those right here. Basically, forward-backward sweep is very much fundamental circuit analysis, but it's quick, it's efficient, works very nice. The method is actually outlined in William Kirsting's book, Distribution System Modeling and Analysis. That's the book I referred to earlier. I couldn't remember the exact title. Very nice book for distribution system analysis, especially for this particular method. The only caveat with the forward-backward sweep is it only works with mesh system or with radial systems. If you have a mesh system, there's some confusion in the algorithm as to where to post the different current injections, so it doesn't work very well. There are ways of making it work, but inside GridLAB-D, whenever we go to a mesh system, we just transition over to the Newton-Raphson current injection method. So this particular one, obviously, it's very similar to the Newton-Raphson method on transmission systems. So you're doing your Jacobian matrix and inverting it and kind of getting a differential solution, or the derivative of your system, and figuring out what the slope to your solution is. It's a little bit different in the distribution implementation, and the references to the particular method we're using are down here on the bottom. It's basically the three-phase current injection method, Newton-Raphson. So it operates under the similar principles as the transmission level one that you may be familiar with, but the specific details of how it's implemented are slightly different. But the basic way to look at the two Powerflow solvers is if it's a completely radial system and you want a fairly quick solution, forward-backward sweep works well. If there's any chance that there's a mesh system, or if you want to do any reliability concerns or anything like that, the Newton-Raphson system is the one you want to use to solve your initial power flow, or all of your power flows, rather. So the forward-back sweep method, just to get into a little more detail, it's also referred to as the ladder solver. You're basically working your way up and down the tree of the distribution feeder and either calculating the current injections or solving for the voltage at each step, depending on which particular path you're on, if you're in the forward or the backward, or I guess the up or down ladder, depending on how you're looking at it. This is one of the first methods to develop for unbalanced power flow. As I mentioned, it's very much based on just simple circuit analysis, which is nice in that regards, that it's an elegant, simple solution, and it's easy to follow. As a result, it's a fairly efficient algorithm. It does take a little while to converge if you've had a very, very large change on your system, but since it solves fairly quickly, that isn't much of an issue. It'll iterate a lot more times, but you'll get to the solution just overall a little bit faster. Again, on the problems with it, it does not work on what we call either a networked, unlooped, or a mesh system. Just the solver runs into some issues of how to propagate the different values and how to solve it. So if you use it on a mesh system, it should warn you, but you may end up with some weird answers. Another thing is, Newton-Raphson has been predominantly where we've been implementing a lot of our new functionality, so there may be components or capabilities that aren't in the forward-back sweep method. The biggest one I can think of offhand is the reliability module does not work with forward-back sweep, and then the component we're adding right now for what we call delta mode, it's basically sub-second dynamics, that will not work with forward-back sweep either. So just one of the things to keep in mind when you're studying particular systems, there may be a reason to pick either forward-backward sweep or Newton-Raphson, and it might just come down to the components of the system, not necessarily the topology. But overall, it's a very good, quick solution method. It works very well, but there are, of course, minor limitations in terms of mesh systems and certain equipment pieces. So if we go over a quick example, this is actually the IEEE 13-node system, and show just basically how it goes about solving it. So on the backward sweep here, I can never remember which one I consider forward and which one I consider backward. You're basically starting with either an assumed or known voltage, so just whatever happens to be the voltage at that point at that time. It may even just be your flat start voltage, so everything's at nominal, and you'll calculate the current consumed by each load on the system. So say, for example, you have a load on node 634, and it's composed of this particular constant power composition. So you have 160 kilowatts and 110 kilovars on phase A, and then 120 kilowatts and 90 kVARs on both phase B and C. So you go through the calculation. You start with just your nominal voltage, so VA, VB, VA, VB, VC. These are actually, if you convert them into polar form, it's basically 2400 volts at 0 degrees, 2400 volts at the minus 120 degrees, and 2400 volts at 120 degrees. So this is a flat start condition. So then you just use your normal Ohm's law relationship, or your power equation. So your current is given by the apparent, or the overall power divided by your voltage, and then the whole thing conjugated, of course, because you're doing with complex numbers here. And you'll end up with your current injections for that particular load value are 66.6 and real amps, and then 45.8 reactive amps for phase A, and so on and so forth. And this basically will occur for every point on the system, and it'll update for every iteration of the Powerflow solver with whatever these new voltage values are. So if you look at the backward sweep, basically you're figuring out what the load is on all of the system. You're figuring out those current injections at each one of those points. And then you turn around and you aggregate those and start to sum them up, moving up the branch. So the backward sweep is basically you start at the lowest point on the system and you kind of work your way up to the highest. So in this particular case, you're basically going from your end-use devices all the way up to your subtransmission or your feeder node, or head of your feeder. So you start summing these up along the branches. Eventually you'll get to the point where branches converge, so you'll sum all of those, basically like their individual spot loads converging, and add up all their current injections. And you'll do that all the way up to the top of the feeder, and eventually get your overall current injection on the system. And then you turn around and do the forward sweep, which is basically you take those calculated currents at every point on the system and you apply them to the impedance between 2 points of the system. So if there's a line here, you'll have a particular voltage drop associated just with the impedance on that particular line. So you'll start with your reference voltage here, and then you'll add, or basically you'll subtract off the voltage drop here, and you'll end up with your new voltage at node 632. And you'll do that across all the different laterals of your feeder. Just basically work your way from the top down to the bottom. So the forward sweep is top to bottom, and then the backward sweep is bottom to top. So that's why it's typically called like the backward forward sweep. I always call it forward backward sweep, but it's honestly the other way around. And so after you've done that through your first pass, you'll have all of your new voltages calculated at different points on the system. And this is just a function of those voltage drops on the lines associated with the current flowing through it. Now you'll do another pass where you basically recompute the currents with that new voltage value, propagate them all the way back up to the top of the feeder again, then do that forward sweep and recalculate your voltages. And you'll keep doing that until your voltage is within a certain convergence criteria. So you may iterate a few times until the voltage at every single node is, say, within 1% of the nominal value. So for 2400 volts, it'll be whenever your different sweeps of the forward back sweep or the backward forward sweep algorithm, you'll end up with a node voltage that's 2 volts or less than 2 volts of a difference from the last guess you tried. Obviously, you can adjust that convergence criteria depending on how stringent you want your convergence to be and how accurate you want your system representation to be. GridLAB-D also has the ability to specify individual convergence checks. It's not supported anymore, but we used to have a Gauss-Seidel solver in here, and one of the ways to actually get that to work better was if you put kind of tighter convergence criteria on these main trunk nodes, and then kind of the end-of-line ones, you put looser ones, you could actually get faster convergence on your system. So that's still a trick you can do with forward back sweep and even the Newton-Raphson one. It's typically not necessary, but if you knew you were more interested in like node 632 and 671 and didn't really care what the voltages at 611 and 652 were doing, you could loosen the convergence criteria on those particular nodes and maybe reach your solution point a little faster. It may not seem like much, but if you're doing a year-long simulation, saving 1 or 2 seconds here and there might prevent your simulation from taking 4 days. It might only take 3 days. So the other particular solver we use is the Newton-Raphson method. And this is something you may be familiar with from transmission studies because it's used quite a bit there. It's still very similar to forward back sweep in the fact that it's based off of power injections and current injections, so you're still injecting your load at every node. The traditional Newton-Raphson method was all power-based instead of current-based, so you were basically looking at how the voltage was varying with a real and reactive power injection at each node. And that's not quite the same method we use inside GridLAB-D, since we use the current injection method, but we'll go over the transmission level one here just briefly, and then we'll get into the actual GridLAB-D implementation. So, of course, the advantage of this is it's using the Jacobian, which will get you to your solution faster, but of course you're inverting a matrix, so that's computationally expensive. So the overall Newton-Raphson method, I won't go into this in too much detail, but basically you're figuring out what your change in power, both real and reactive at each node is, and associating that with your Jacobian matrix to get the change in the voltage magnitude and the voltage angle. And you'll just iterate through that until, on your traditional Newton-Raphson method, your delta P and your delta Q for each iteration are within a certain convergence criteria. So if we did just a simple transmission example with like a 3-node system, you go through all of your various steps, just basically get your initial voltage, your Jacobian, and then whatever the power difference or the power injections are at those nodes, and then get your updated voltage value, and keep doing that several times until you eventually end up with a final solution. This is just kind of the progression for a particular node. So you have your voltage 3, just how the amplitude is changing, and then the angle on your particular system and how it's evolving with time. Again, this is how the traditional one works. If you want more details, pretty much any power systems book ever printed will have this in there in one way, shape, or form. The one we actually implement inside GridLAB-D is a slight variation on the Newton-Raphson method called the Newton-Raphson current injection method. And rather than using power injections, it actually changes it to be very similar to how the backward-forward sweep algorithm works and changes them into current injections. You're still updating your voltage values. It's not the angle and the magnitude anymore. Now it's the real and reactive portions. But you're doing it with another Jacobian matrix. It's just a slightly different form, obviously to account for the fact that you're doing real and reactive current injections. And if you want the angle and the magnitude, obviously you just have to convert from the rectangular coordinates into the polar coordinates. So you're still getting the same answer. You're just approaching it a different way. The advantage to the current injection method, I thought we had an example, but we don't, is since a lot of the distribution loads are kind of modeled on that Zipp fraction, it's very easy to convert them into a current injection and then update that current injection as your voltage is changing on the system. The other nice thing about the Newton-Raphson method is since it is Jacobian-based, it is factoring in kind of the slope at a particular solution point for those different Zipp fractions, so you may have to iterate less. Obviously, it's a trade-off. The forward-backward sweep one will iterate a lot more, but it's a much simpler power flow, so it iterates faster. So you'll have more iterations, but quicker time, whereas the Newton-Raphson will require fewer iterations, but there's this great big matrix inversion in the middle, which eats up some computational cycles, so fewer iterations, but slower. I don't know what the break-even point is. I've never actually looked at it, but I would imagine there's a particular system size where both of them are the same, and then if you go to a bigger system, forward back sweep might be faster or slower, or Newton-Raphson may be faster or slower. So a lot of times, as I mentioned earlier, your solution method just comes down to topology concerns, or if there's a particular functionality or equipment piece inside GridLAB-D that dictates you use one form or the other. So time series simulations is basically where all of the really useful things come out of GridLAB-D. Just as a static power flow solver, it is useful, but the big advantage of GridLAB-D is, on the whole, is the time series simulations. If you want to look at how a house behaves with varying voltage, or if you want to look at a system behavior over the entire day, obviously you just want to do some form of time evolution of those, or how the system will react to particular conditions. You don't want to just do one static power flow and say, yep, this is the answer, I'll derive everything from there. That's traditionally done but it was more for like very simple planning studies or peak capacity planning, where you just get your single value of the load, and that may be your peak demand at 5 p.m. or something like that on your feeder, and that's what you use for all of your planning level studies. But if you want to capture the more explicit behavior, or especially look at some of the things like Jason mentioned earlier with CVR, if you reduce the voltage on your house or your water heater, it's going to take longer for that particular BTU count to still get into the device. So while your overall power may go down, your energy consumption is still going to be the same, or may actually be higher or lower depending on what the system is doing. So a good thing to look at, to remind people of here, is these are a series of Powerflow solutions. This is what we like to call quasi-steady state. So it's basically a snapshot at each instance in time, but you're updating those state models and particular aspects of your system with different periods in time. This is not a dynamic or an electromagnetic simulation like you might experience on a transmission level, particularly if you're using something like PSLF or what's the other one? PSSE, yes, the PTI solver. I couldn't remember what the name of it was. They'll do the static power flow as well, but then they also transition into the dynamic solver, where they will give you kind of the sub-second value of how your individual machines are behaving. This particular module, the Powerflow module, does not do that. It only does down to a second level or higher, depending on what you're looking at for your minimum time step. We are adding in the capability to do these dynamic level simulations, but it's not explicitly part of the Powerflow module itself. It's kind of an over-encompassing capability we're adding right now, but it's going to be part of the 2.3 and 3.0 build, so it's not even in the one that's included with this course material. But just something to be aware of if you're looking at simulations that might need that capacity. So if we go back to the... this slide might have been in the first presentation, I can't remember. But basically how GridLAB-D works is you're doing these quasi-steady state updates on the system, and basically this delta T will be dictated by whenever a particular agent in the system wants to update. So for this example, each one of these little vertical slices is a time step inside GridLAB-D. So at each one of these vertical slices will be where the power flow reiterates and gives you a new solution. And that may be dictated by various states on the system. Maybe things are going to change at particular time steps, things of that nature. So if we look at the IEEE 13-node system again, if we want to look at a time series simulation of it, you can basically specify either this capacitor to follow a specific voltage and then put in a player or a scheduled transform or anything like that that will adjust the voltage or the load on the system. Or you can actually go in and populate this feeder with houses, which is what we did here, and then let the house behavior determine how the voltage is varying on the system and look at those impacts. So in this particular case, if we do a time series simulation, this is just a one-day simulation with, I want to say, about 300 houses on the IEEE 13 node. I can't remember exactly. It's actually in the demos or the examples folder that was part of this module's zip file. So if you want to look at the explicit ones, or we can do it afterwards. But basically, as the load is changing throughout the day, you'll see the voltage is kind of varying, and there's these discrete jumps here and there, which are associated with the regulator changing position. So as the voltage gets down below a certain point, say 2150, I don't know if that's the exact set point, the regulator will actually adjust its tap settings to keep the voltage within the deadband. And that's just showing you kind of that multi-state idea and the evolution of voltage with time, just so you can capture the explicit system benefits or impacts. I mean, the IEEE 13 node is obviously a fairly simple example, but you could see how if you wanted to do a planning level study, if you had representation of your load throughout the day, maybe your voltage wouldn't jump up like this. It would continue to go down and then rise back up later in the afternoon. You could add a regulator into your system using GridLAB-D and see what kind of benefit it might provide you, and take that back to the utility commission or whoever your governing board is and figure out if they can fund to add in an extra regulator or anything like that. That's the real flexibility in here, is instead of just doing that static power flow, you can actually do the time series of static power flows, which we call that quasi-steady state, and capture the overall system behavior and see that, okay, if we add this regulator, we never drop below 2100 volts on node 671, and that might be keeping you within an operation band that you're required to maintain. So how does it all work? I've kind of alluded to this off and on, but basically the entire distribution network breaks down into two different types of objects, nodes and links. So everything, well, pretty much everything inside Powerflow is either a childed class of a node or a link object. So basically things like overhead lines, underground lines, transformers, regulators, they are all links, so they're connecting two different buses or two different nodes. Anything that's like a bus or a spot load or kind of a connecting point is a node in the system. And then just kind of a quick overview of the two different power solvers here again. Basically, the voltage is at the nodes, the current gets propagated through the links in the sweeps, and eventually you update the current injections and the voltage until you get to a point of a voltage. This is zero voltage error, but you get to your voltage convergence criteria. Newton-Raphson works fairly similar. Basically, you're building up your admittance matrix and forming your current injections and solving for whatever the voltage difference is based off of those current injections. And again, you're solving it until you get down to a voltage error of 0, or whatever your convergence criteria is. Just kind of a quick little note here, if anybody's familiar with the Super LU project, that is what we are using as our matrix inversion utility inside GridLAB-D right now. There are provisions for hooking in external ones if you have a different preferred matrix inversion technique for the Newton-Raphson method. So the PowerFlow module itself, when you're going to put it into your GLM, you obviously have to declare the module PowerFlow at the top of the GLM, and we'll show an example of this later, just to get all of the objects loaded in and allow the use of them inside your GLM. There's a few things that we call module level directives. They're basically global settings for that particular module that'll dictate how it handles all of the objects in there. In PowerFlow, the key one is the solver method. You can either do FBS, which is the default one, which will do forward back sweep, or NR to do the Newton-Raphson. If you don't specify a solver method, if you just do module PowerFlow and then put a semicolon at the end and don't have any of these braces or anything, it'll default to the forward backward sweep method. If you want the Newton-Raphson one, you have to explicitly put the solver method NR in there. These other ones are kind of a global convergence criteria. So the default maximum voltage error is 1e to the minus 6. So to multiply that by whatever the nominal voltage is on a node and use that as the default convergence criteria. You can specify it individually on the nodes, but this is just kind of a starting point for the whole system to work from. The NR iteration limit and NR Super LU procs is a specific directive for the Newton-Raphson solver. Basically, Newton-Raphson has an internal iteration loop as well as the GridLAB-D iteration loop. So this NR iteration loop limit specifies the number of internal iteration count that Super LU can do before it goes out to a GridLAB-D iteration. Honestly, most of the time, nobody will ever have to mess with this. The NR Super LU procs is the number of processors that Super LU supports. It does theoretically support multi-threading. I have never seen very good results come out of that, but you can conceivably tell Super LU that you want to use 2 or 3 processors and it will invert your matrices a little faster. As I mentioned, it's kind of mixed results on there just because I think the particular matrices we're feeding into it don't implement in a parallel fashion very well. It's still being improved, so there still are ways to speed it up, and this may actually get folded into the overall GridLAB-D parallelization at some point in time. But for now, if you want to try using more than one processor just for the matrix inversion, if your computer supports it, you can specify that through this module level directive. And again, just kind of highlighting the overall differences between the two solvers. Forward backward sweep is a faster solver as implemented, but Newton-Raphson handles mesh systems, reconfiguration algorithms, and reliability. So it has more of the functionality built into it, especially if it's built off of a mesh system. But for the most part, the two solvers are equivalent in terms of their functionality and what objects work with them. It's just there are specific examples where only Newton-Raphson works. For like reliability is the best example. So objects in the PowerFlow, we've kind of beat on this several times, but it basically breaks down into a node and a link object is what everything is composed of inside PowerFlow, with the exception of what we call library objects. And that's things like the line configuration, line spacing, transformer configuration, and regulator configuration. These are more kind of informational definition type objects where they're not changing with time, they're not directly involved in the Powerflow solver itself, they're just kind of specifying information about the particular object. So the best way you could think about something like these line configuration, line spacing objects is you could have like an object motor inside GridLAB-D, and then this would be like the nameplate information that goes into the motor. So it's still needed to actually make the object and make it solve properly, but it's not explicitly part of the Powerflow solver itself. So the forward-backward sweep calculation is done at the node objects and link objects. The node objects are obviously updating their voltage, and then the link objects are accumulating the current injections. Just kind of some examples of what falls under the category of node versus link. Node object is a capacitor, load, meters, triplex meters, frequency generation, emissions, current dump. Most everything you'll use for generic power flows is kind of just the load, the meter, the node itself, and then maybe capacitors. A lot of these other objects are kind of special controls or special implementations that will do either a particular type of functionality or allow you to extract a specific piece of information. But at the end of the day, they are technically a node object, so anywhere you use a node, you should be able to substitute one of these objects in as well. Link objects are kind of the connection points between the different nodes. So obviously your conventional things like overhead line, underground line, and then triplex line. Triplex lines are for that split phase system that we use in North America for the final push down to your end-use load, so the plus or minus 120 for the 240 overall. We have a special line type for that that helps capture some of the capacitive effects. Regulators and transformers. Then there's things like series reactors, reclosers, relays, switches, fuses, things that are in there that aren't used quite as often, but they still have the functionality. And a lot of these things like reclosers and sectionalizers really don't do a whole lot in terms of the base power flow, but they interface with like the reliability module if you want to do reliability studies on your system. So if we look at just a sample node inside PowerFlow, this is a lot of the default parameters that are published. I'll caveat this with you do not have to specify all of these. These are just the ones that are available for you to specify when you're writing up your GLM. You don't have to explicitly put A, B, C, A, B, B, C, C, A, and all those different things. The main one you'll have to specify is nominal voltage, which ironically enough isn't even listed on here, and then the phases. And it looks like we have a question or something.
Yeah, the question is, what is the frequency generator?
Frequency generator is a highly development stage, experimental, please don't use it, thing that was put into GridLAB-D to do a rough approximation of system frequency. So basically you would attach it to either the head of your feeder or your swing node on your power flow, and based on how the power is changing on the system, it would provide you a rough approximation of how the system frequency is adjusting. It's highly experimental and very lightly tested. It will give you a very, very crude approximation of how system frequency is varying, especially if you wanted to do kind of some steady state level microgrid type implementations. I would hesitate using that. I would actually wait a month or two here until I get the microgrid stuff working, and then we'll have the dynamic level and a kind of, we call it a super second equivalent form of the dynamics in there, where you'll calculate the frequency in a much more traditional fashion and it'll be a lot more accurate. Basically, that frequency gen object only does the simple swing equations and kind of calculates the frequency deviations based off of that. So it'll give you a very rough approximation of how the frequency varies on the system, but it's highly experimental. It hasn't been tested very much, and it seems to work, but if you throw it at a really big system, I can't guarantee that it'll actually still provide you meaningful results. And it hasn't been tested in a couple years, so I don't even know if it still works, honestly.
Yeah, I would say it's one of the things that's really good for if you wanted to do a proof of concept to show that, like, you know, maybe like what we call grid-friendly appliances or grid-friendly controllers, you know, appliances that respond to frequency. It's a very good way of doing just a proof of concept. Beyond a proof of concept, I would not take it with that model.
No, and it is only like I said, it's a simple approximation of frequency, and it is only the fundamental frequency. It's only the 60 hertz or the 50 hertz, depending on your system. It won't do any harmonic analysis or anything like that. None of that should even be implied in there. If we look at kind of an extension of node, an object load, so whenever anything is what we call a subclass of either a node or a link, it'll have all of these published properties that a node has, as well as its own special properties. So every single one of these particular parameters is available to load, even though they aren't explicitly listed. And then you'll have things like constant power A, constant power B, constant power C, constant current, constant impedance, and that's basically defining those zip components that we went over earlier. There's some additional functionality on here that we'll try and demonstrate later today that allows you to specify the fractions and the percentages directly instead of having to convert it into the complex format. The whole beginning of the presentation we were talking about zip fractions in terms of a percentage of the whole and a power factor. For this particular object with these published properties, the constant power A, constant power B, and everything like that, these are the complex representation. So you can't specify like 300 VA with a power factor of 0.95. You actually have to change it around into the 280 real or kilowatts plus whatever it is, 100 and some reactive, whatever the fraction actually converts out to be. I don't have my calculator, so I'm at a loss here. But you can also define some bookkeeping information. I hesitate to call it completely superfluous, but you can specify the load class. So if you're doing an aggregate load and you want to help classify which ones are residential, which ones are commercial, and everything of that nature, you can specify an enumeration on there that lets you group it. This is very similar to the group ID, but it's exclusive only to loads. To my knowledge, the only place this actually has any functionality is inside the reliability module. Depending on the type of fault, if it's an industrial or commercial load, it drops the entire load. If it's a residential, it'll only drop a particular phase if you have a single phase fault. But other than that, it's purely informational in nature. Object meter is another subclass of node, so all of those same node properties fall into it. This is pretty much exactly what it says by the object name, meter. So if you want to record the power or the current or the voltage anywhere, meter is the best way to do it. Obviously, the voltage is available everywhere, but if you want to get the current draw at a particular node, or more importantly, the power consumption and energy consumption at a particular node, you'll use an object meter. And that'll give you things like your measured real energy, reactive energy, the overall power, and then the real and reactive portions. These measured voltage quantities, you can use those. Those are the exact same thing as voltage A, B, and C from the node, so they're just kind of a duplicate just for convenience. And of course, these are the interaction point between some of the other modules. Meters are the interaction point with commercial and generator, as well as the triplex meter, which we'll get into here shortly. It's just a slightly different form. That's where a lot of your other objects, like your houses, if you have a wind turbine or an inverter, they'll interact with a meter typically. You should be able to connect them to a node or a load, but a lot of times with those type of additions to the system, you're looking for the specific power consumption at a point, or you want to somehow track that, so you'll attach them to a meter. Triplex meter is just a special form of node. The only difference is this only works when you have that split phase configuration, so if you have an S in the phase. Again, that's the North American convention. I don't know if it's really used anywhere else in the world, but we had to define a special meter for it to make sure that it accumulates your power consumption and your voltages and everything correctly. Triplex meter is primarily the connection point between your residential homes and the Powerflow module. And one of the nice things that's been added into here is it'll also include some billing information if you put it in bill mode. So if you want to get kind of a rough idea of how a customer's bill may be impacted by whatever distribution technology you're testing, you can apply that functionality to the triplex meter and get kind of a rough idea of how their actual electricity bill will change. I believe that functionality is in the meter as well, but we predominantly use it on the triplex meter side. So then the overhead line, which we went over a little bit earlier, basically these top parameters up here are common to all link objects. So the two from, phases, and name are inside every single link object we'll go over. And then something specific to line objects, so overhead lines, underground lines, triplex lines, things of that nature, you'll also have your length and your configuration. And if you remember, the configuration is a separate object or a separate series of objects, and that gives you kind of the physical parameters of the system. What's the size of the conductors, where things are actually oriented in terms of where they are on the pole, or how far they are from the ground, things of that nature. As it says down below here, the underground line and triplex line follow a very similar format. The only difference is the configuration might look a little different, especially in terms of the conductors. They have different information. And then configuration and length determine all the relevant matrices. So basically it's that slide we had way back near the beginning where we had the picture of the distribution line. It got converted into the little schematic diagram, and then that got converted into the 3x3 matrix. So with all of this information, you're basically collapsing what is a physical overhead line down into a 3x3 matrix that the Powerflow solver will use. So the line configuration has a couple of different ways of using it. The way we showed it earlier, it was specifying the different conductors and the spacing. Another way you can do it is if you have the direct impedance values, especially if you're dealing with some of like the IEEE test systems. They will give it both in the physical layout of the system, but it's in a separate document, so it might be more convenient to just put in the impedance values directly. You can put those in there, and that specifies your ABC impedance matrix directly. Something to be careful on this. This is kind of a feature we added in for convenience, and it has been used a couple times, but it hasn't been rigorously tested, so you may run into some issues. The line objects are expected to be defined using the line configuration in terms of the conductors and the spacing. You can use this, but we haven't tested it, so you may run into a situation where it behaves not quite as expected. Transformer, again, very similar to other link objects. Everything up above, it should be in here with like phases, name, and then the to and from you still have to specify which nodes it's actually connected to. The configuration gives you the information on the transformer itself. This power in and power out, this is not exclusive to just to transformers. This is a link property, and basically it allows you to look at the power coming in and the power going out of a particular device. And the in and out is determined by the from and to, assuming the power is going from the from side to the to side, if that makes any sense. So if you have any type of reverse power flow, you'll get like a negative power out and a negative power in type thing. And if you take the difference of those two, you'll get the power loss on that particular line, and there's actually a separate property for that as well. But if we look at more of the details of the transformer configuration, this is where you specify not only the size and kind of the impedance values, but also the physical connection of the windings. So we have implemented inside GridLAB-D right now, we have a YY or a star-star, delta-delta, or a delta grounded Y, and then a single phase. So this is still just a single phase as in like an A, B, or C. And then we have what we call the single phase center tapped. That is the one that goes from the ABC notation down into the North American standard of the line 1, line 2 neutral. And in this install types, this is very similar to the load classification that we went over earlier. This is purely for informational purposes at this point. I think one of these might be used in the simple transmission or transformer thermal model we have implemented, but outside of that, they're primarily there just so you can keep track of where that particular transformer might be located, or if you want to use it similar to like a group ID. So if we look at the actual transformer configuration, this is common to all of the different types of transformer. It's just how you specify these parameters may be a little different depending on which particular type you're implementing. But you'll end up with your primary voltage and your secondary voltage, so that's just to define your taps ratio on your transformer. Then, of course, the power rating is the overall rating, either for the individual phases of your transformer or the overall, and then it'll basically split it between all three phases. And then that's used to basically convert from your resistance and reactance, the per unit values, into the actual impedance values for the Powerflow solver. You can also specify the impedance directly, and then there's also this impedance 1, impedance 2, and shunt impedance. These are used for the split-phase center tap transformers, and the shunt impedance especially if you want to specify shunt losses. So if you want to get your underloaded transformer losses or anything like that, this is a good way to specify that. As a caveat over here on the right, it's only used in the center tap and YY transformers. We don't have shunt losses in anything like the delta-delta or delta-grounded Y or any of those transformers yet. So the regulator, again, kind of a special case of the transformer. It's like an ideal auto transformer, basically. Get all your same link parameters, configuration. Some of the other interesting parameters inside the regulator are the tap A, B, and C. So that just dictates the tap position for the regulator itself. So whatever your turns ratio is will be dictated by whatever position a particular tap control is in. And then if you're in one of the remote operating modes, if you're either in the VAR control mode or the volt or even the volt VAR, this sense node or sense object will tell you which particular device you're looking at to determine when to change the actual taps on the regulator. Again, similar to the transformer configuration, and I think I already covered all the rest of that. So the regulator configuration, we went over this a little bit earlier, but basically all the different parameters to make your regulator behave like the physical object. So your band center, bandwidth, the number of taps you can raise or lower the system, and then depending on your mode, so if you're doing line drop compensation, your current transducer ratio, power transducer ratio, and then your impedance values associated with your compensation, those will get specified there. The phases that your current and potential transformers are attached to, regulation of the regulator as a whole, that helps determine kind of how the voltage changes with these taps and your overall bandwidth band center, and then the different control types. The type A or B, I believe, is only actually supported inside forward backsweep right now, and you can refer to William Kirsting's book to figure out what the differences between those are. It's just basically how the physical windings are actually connected. And then this tap position A, B, and C underneath the regulator configuration, these are just the initial tap positions. I think these are the initial. Either these are the initial or these are the final, and then the other ones are the initial and these are the final. But between this and the ones that are actually in the regulator, they represent the tap position of the system. These, I'm pretty sure, are just the initial tap position, and then the time evolving ones as the system's actually changing are the ones under the regulator object itself here. So then if we wanted to do a node-to-node connection, that's where the links are used. So if we want to do like an overhead line object between node 1 and node 2 of a system, this particular one says it's a 3-phase line in a delta configuration, so there's no neutral. And you're going from node 1 to node 2, and it's 2000. GridLAB-D, if you don't specify a unit, it assumes whatever the object is specified unit is as the default. For overhead underground lines and pretty much all lines in general, we assume it's in feet because we love the imperial system. If you specified this thing in like 2000 and then put an M afterwards, so you want it to be 2000 meters, GridLAB-D is smart enough that it'll convert that into the internal designation of feet and automatically handle it for you. The other way to connect two different nodes is through what we call the parent-child connection. So that's basically a zero-length line where they're effectively the same point on the power system, maybe even at the same bus, but maybe you want to separate them out for either modeling convenience or just as a way of connecting it so you can monitor specific aspects of how things are being consumed. So the best example of a parent-child is if you want to connect multiple loads to a particular node, or if you want to connect loads to a meter, or a really good example where we've done this is if you have like a house and distributed photovoltaics on the system. You might have the meter for the house, and then you'll have a separate meter for the photovoltaics. Well, they still connect to the exact same node on the actual power system, so you'll put basically your object meter for your house and then your object meter for your photovoltaic, and then you'll parent those to the same common node, so the PowerFlow solver still handles it all the same, but you'll have your individual power consumption or power generation monitored for whatever particular study you're looking at. Something I should caveat on this real quick, even though I think we might get into it later, is the parent-child relationship. If you do forward backsweep, you can conceivably chain this on forever. You can have zero-length lines down any iteration of a genetic tree, I guess, if you want to. So you can have parent-child, grandchildren, great-grandchildren, and things like that. Newton-Raphson will only allow you to go one level down. So you can only have a parent and a child. You can only have one object parented to the next. If, say, in this particular object, we have node 2 parented to node 1, we could not parent node 1 to anything else, otherwise the Newton-Raphson solver doesn't know how to handle it. So just a quick caveat in there. Generally, when you get to the point of having quote-unquote grandchildren inside your nodal structure, you can actually rearrange it and get it implemented in a different fashion, so you don't need that level of nesting, for lack of better words. So if we look at a simple feeder example, this is one of the IEEE 4-node feeders. It's basically a way of testing different transformer types. And if you look at it, it's a system of nodes and links. So each one of these vertical lines is a bus, just like the transmission notation. And the points in between them are links. So inside GridLAB-D, each one of these vertical lines is a bus or a node, and each one of the connecting points, or the connecting lines, is a link or some form of line. So in this particular case, I believe these are all overhead lines. So this is an overhead line of 2,000 feet in length. This is an overhead line of 2,500 feet in length. And then there's a transformer in between nodes 2 and 3. And we will look at the difference there. I can't remember. Yeah, it's not in here. So let's see if I can find the example here. Should be this one. Yeah, this looks like the right one. So basically, this GLM file is the exact same thing as this one-line diagram. It's just represented in GridLab form. So as we see, we have our clock up at the top if we wanted to do any type of time series simulation. You have your Powerflow module directive. In this particular case, we're telling it to start with the Newton-Raphson solver. And then you have your library information. So this specifies the conductors used in your overhead lines, so the information associated with those, and then the spacing of your individual conductors, and then the overhead line configuration, just saying where they are on the pole and how they're spaced and all the different components of it. And this is related to the physical parameters of the system. In this particular case with the IEEE 4 nodes, this is actually in a separate document. I think it's in an IEEE transactions article, actually, where they have all of the line configuration information specified. Then you do the same thing for the transformer. Give it the name, the power rating, the individual phase ratings, the turns ratio. This connect type is either an enumeration in terms of the actual text string or the number directly. A type 1, I believe, is a YY, but we can check on that real quick. I don't know if you guys got into this last time, but you can use the mod help command. So if we look, 1 is a YY transformer right now. So if we want to change it to, say, a delta-delta, we change that transformer type to 2, or we can actually adjust this so it says YY. So that's the same thing as putting a 1 there. And then, of course, it's specifying your turns ratio, as I mentioned, and then, of course, your impedance values associated with it. Then you get into the actual implementation, and you have your nodes. So node 1, which if we go back to the system, is your infinite bus or your swing node. Forward backsweep, you don't have to explicitly specify that. It doesn't hurt anything if you do. Newton-Raphson requires you to tell it which one of these is the swing node. If you don't specify a swing node, Newton-Raphson will actually fail out and error for you. Then the phases is just the particular phases that are connected at that specific node. And then this voltage A, B, and C, these are the initial values. So you actually don't have to specify these. The only one you have to specify is this nominal voltage to tell it what voltage area you expect this node to behave in. And that's mainly to make sure that when you connect two nodes, like node 1 and node 2 here with this transmission or this distribution line, that you're not mismatching your voltages without a transformer. But if you don't specify the voltage A, voltage B, and voltage C, it'll assume a balanced configuration for the initial power flow solution and just take it off of this nominal voltage. However, if you want to start at an explicit voltage, or if you wanted to change this voltage with time, say if you had some phasor measurement unit data or some SCADA data at your feeder substation, you could play that into these individual values and change the reference voltage at every single power flow iteration. That's only true for the swing node. Everywhere else, like if we go down to node 2 here, this is again the initial solution, but if you played in values of voltage A, voltage B, and voltage C into the solver while you were solving the power flows, the power flow solver itself will actually override those for the subsequent nodes. Only the swing node can have the voltage changed after the initial power flow. Otherwise, the power flow solver itself just overrides it. But again, we have our overhead line connecting node 1 and 2, just like the diagram shows. So you can see it's a 2,000-foot line, and that's what we have right here. And then the line configuration, all of these lines are the same thing, so we only have one line configuration. Then the specific transformer, all of the information was actually in the transformer configuration, so all we have to do is tell it what the phases connected are and where it goes to and from. And then on the other side, you notice this particular transformer was a step-down transformer, so it went from 7,200 volts down to 2,400 volts. And then your initial conditions. Something else I should caveat that with is this is only used pretty much for the convergence criteria and the initial conditions, and then some simple checks. In this particular transformer, if you look at the way we specified it, it's a YY going from 12.47 kV down to 4.16 kV. Well, that's not really what we have written here. So you might get a different turns ratio. This could actually solve to, say, 120 volts or 9,600 volts. This does not dictate what the actual power flow solution will be. It just gives you the initial starting condition. The transformer itself and the overall power flow will still solve to whatever voltage is appropriate for that system. So you could specify this completely off the wall. It's just as long as it matches with anything else connected by a normal link. That's the only caveat on there. So it's good to keep it with what the actual system is, but if I changed both of these to 12 volts, the system wouldn't care. It'll iterate a little bit more because the initial condition will really be horrible, but overall the power flow solver won't care too much and it will still go to the correct solution.
Frank, maybe this would be a good point to actually maybe add an output file to this and actually run it, show people how to run it.
I was just getting ready to run it. But to add an output file, we have a couple different options. In terms of what you can do with the output file itself and in terms of what you're actually using to generate the output file. So I'll show the simple one first. So I'm going to cheat here a little bit, and I'm going to get the current directory because I'm not in it. So I'll change to that folder. And inside here there should be the IEEE 4-node GLM, which is the one we just modified, has today's date and everything on it. So if you just want to run it as is, you just do GridLAB-D IEEE 4-node.glm. And if you run it, since we aren't specifying an output or anything of that nature, it runs, it gives an answer, and then that answer disappears into the ether, and you get nothing out of it. But from GridLAB-D's perspective, that's perfectly fine. So one of the easiest ways to get an answer out of GridLAB-D, especially if you're only dealing with like a static power flow, is to specify an output file. So you can either do, I think it's -o or --output, and then give it an XML output. So we'll call this IEEE 4-node test.xml. Well, if we run that, it doesn't look any different from the running perspective, but if we go back to the folder, we now have this XML file. And theoretically, if everything is linked right, you can open this in like Internet Explorer and it'll have a style sheet and it'll look all pretty. And it works. Half the time this doesn't work, so if you open this up and it tells you it can't interpret it, the good news is that the information is still there, so if you look at it with any type of XML reader, you can actually go down to the individual nodes and find all the answers, but it's a lot easier to read when the style sheet actually works. So here, if we go down and look at the outputs, we'll find out what the solution voltages were here. So if we scroll down a ways, so it'll give you a lot of information about the actual system you just solved. So it'll tell you the bus type. So one of them was a swing, the other two were just PQ nodes. And you'll notice there's only 3 of them here. The way that works is it's actually broken out into the 4th object is actually a load object. So it's further down here. So you have to be kind of careful in that. Even though it is a 4-node system, one of the node objects is actually a load, so it's printed in a different spot. But then if you look at the other things, it'll tell you what the voltage error was used for the convergence criteria, what the final values were. So of course the swing node is at the plus or minus 120 because we're not specifying anything different. And then if you look at the other nodes, obviously there's a little bit of a voltage drop here, so the magnitude's a little bit less. The angle's shifted a little bit. And then after the transformer, it's dropped down to 2200 volts instead of the 7100 volts. And then if you look at some of the other information, if you wanted to look at the delta voltage values, those come out. Excuse me. And then something to be careful is a lot of times you'll see these current A, power A, shunt A. These are only if you are specifying some form of direct load on the node, which we highly encourage you not to do. If you're going to apply a load to your system, it's best to use the object load. So these are here, but they generally will always be 0 for a node. If you want to measure the specific current at a location on the system or the power, you'd want to use a meter. And we'll actually try doing that here real quick. But if you go through some of the other objects, like if we look at the overhead lines, it'll tell you where they're connected from. The status is just whether they are open or closed. It's an enumerated value, so sometimes it actually says open or closed in here, and then other times it'll say like 257 and 0. How long they are, and then the power in and the power out of that particular line, or if you wanted the individual phase power in and power out. So that'll give you an idea of how much power is actually flowing in and out of that line, and then how much is being lost just due to the resistive and inductive losses on that particular portion of the system. And then there's some information about the flow direction. So everything is flowing in the forward direction. So if we look at our original system, we are just flowing from 1 to 2 to 3 to 4. If you had like a generator down here and it was actually flowing from 4 to 3 to 2 to 1, you would see an R on these indicating that it's a reverse flow condition. So we consider forward flow going from the from side of the line to the to side of the line. If it's going the opposite way, this should indicate an R instead of an F. And it gives you the individual phases. So you could have like phase B and C going forward, and then suppose phase A was going in reverse, it would indicate that for you. And in the load information, well, there's the transformer first, and it's basically the same information that was on the overhead lines, and then a little bit of extra information. Well, actually not on the transformer, I'm sorry, I was thinking of regulators. And then the load, of course, tells you the specified values, the real and reactive portions, and then if there are any other portions of your load specified, which we didn't in this particular case. And then some other objects which we don't actually have in the system. So if we wanted to look at the overall power consumption inside the system, an easy way to do that is to just go down here and say if we wanted to look at the whole thing, we could either look at that XML file output for overhead line, and we'd have to give this a name so we could find it in the system. So we'll do that while we're in here too. Call it out. Hopefully I didn't use that down below. Nope. And then the other thing you can do is we can just change this into a meter. If you recall from the presentation, a meter and a load are both subclasses of an object node. So anywhere there's an object node, you can specify an object load or an object meter, and it will behave the exact same way. It may actually have some additional functionality. So if we do just this solution, again, the GridLAB-D output, not very spectacular. But if we look at the XML, if we refresh it, there should now be a meter object. And I thought this was alphabetized. Oh, there it is. So if you look at the meter object, it's telling you there's no real energy and no reactive energy because we're only doing a static power flow. There's no time evolution or time integration on this. But if we look at the measured power, it'll give us the total measured power and then the individual phase measured power. So it's not terribly exciting for this because we know it's predominantly the load that we specified and then any losses on the system. But if you were looking at a time-varying simulation, or maybe if you wanted to get the peak demand of your system, taking that swing node and basically making it a meter is a good way to get a quick indication of that. And all of that gets dumped into the XML file. Another way you can do this, and we'll see if I can get it to work, is you can do a volt dump object. Never remember the syntax for this, but luckily GridLAB-D has its wonderful little file. So we'll specify volt dump. Oh, that's Powerflow. And then we tell it which group we want, the runtime, the file name, the run count, and then whether we want it in polar or rectangular form. So I'm actually going to copy this, just so I don't have to keep switching back and forth. And then we'll edit this appropriately. So we'll get rid of the class thing, because we want an object, not a class. The group ID, we're not going to specify. We're going to leave it empty, so it'll give us all of them. But if we wanted to say just do the nodes instead of the meter and the load at the end, we could tell it something. Actually, we'll try that just for grins. Is it class equals node? And then the runtime, if you wanted it at a specific instance, if you were doing a Powerflow time series simulation and you wanted to get a volt dump at, say, noon on a particular day, you could specify that here, but since we're only doing a static Powerflow, we don't really care. We just want it to dump. And then we give it the file name. So we'll call this node test out file. And then I'll give it a CSV extension. It just dumps it as a text file, so this way we can open it in Excel or anything. Run count is the number of times you'd like it to dump to that file, especially if you're using that timestamp flag, which we're not, so we don't really care. And then the mode we'll specify as polar, just because it's nicer to read, depending on what you're looking at. Or I guess that's a matter of personal preference. We'll put it in polar form for this. So now if we run this, and we can get rid of that output line if we don't need it anymore. You can actually do multiple outputs, so we could still generate that XML file if we wanted, and also get the volt dump, but it's kind of redundant in this case, so we won't deal with it. So then we run the IEEE4 node again, and again, nothing special pops up here. You have to actually look at your output files and your results to see anything inside GridLAB-D. The interface itself doesn't really tell you much unless there's a warning on the system. So if we open this up in Excel, that's interesting. And it didn't work.
I don't think the group works for class ID.
I think you're right. Yeah. So we're going to get all of the volts just now. This is an issue with volt dump, and more specifically GridLAB-D in general. If you specify the class inside the group selector, it doesn't seem to quite work right. It works if you do a group ID. So if we went in and did a group ID and put it on like node 1 and node 2, we could still use that group field, but for the particular case I was looking for, I guess it does not quite work right. But now we should actually have an output. And we do. And this is obviously opened up in Excel, but if you look at the raw text file, it's just a comma-separated variable format. Gives you the node name, the magnitude and angle, since we told it to put it out in polar format, and it just gives you the voltage values at each one of the nodes. And this is for a specific time. It's January 1st, 2000 at 3 o'clock in the morning. Again, this was a static Powerflow, so that's the only time step it ran. But if you wanted to do this for specific instances in time and then use that run, I think it was run count, you could get a series of these things with the different times on there. But this is a nice way to do it as an alternative to the XML file, especially if you're going to do anything with these values, like if you want to turn around and plot them. It's a lot nicer to get them put directly into Excel or some other form of data management software instead of having to parse out the XML and get the data. Text file is a lot easier to read, at least in my opinion. But that's just a quick example of just a simple IEEE 4-node system and running it in GridLab and then just getting kind of some example outputs from it. Obviously, you could use some of the more time-oriented recording methods. You could use a recorder or a collector, but for a static power flow, it's not really the best use of those particular objects just because you'll get a single static value. In that particular case, a volt dump or just the output file is the best way to go. And if we wanted to run this in forward back sweep, obviously we can just change this into FBS. And then we'll run it. Actually, we'll change this name so we can compare the answers. They should be more or less the same, but there will be some slight differences. So now if we run it again, nothing different on that output, but the output file should look slightly different. So let's see here. Yeah, like the actual values here. If you look at node 2 on both sides, that one's 0.58371. This is 0.54, or wait, yeah, that's the right one. 0.548453. So very, very, very close, but obviously they're two different solvers, so there's going to be some slight numeric differences. So, are there any more questions on just kind of the quick 4-node example here? Otherwise, we'll go forward a little bit here. We still have 6 more slides. Okay. So the output, obviously you're doing a power flow solution, so you'll get the 3-phase voltage at every node, including inherited objects. So if we had a parented or childed load in there, it would give us the voltage for those as well. And those voltages obviously will be the same as their parent. Since you're implying a 0-length line in between the two, there's not going to be any voltage drop. And then for link objects, you can get the power in and power out, as well as the current in and current out. So if you want to look at particular line flows at certain points on your system, or if you're looking at the reactive power consumption down like a particular branch, that's a good way of looking at those. As the XML showed, there's a lot of information inside there. If you did something like a regulator or a capacitor, it'll give you even more information, things like where the specific tap position was at the end of the simulation, or whether a particular switch was open or closed. You can also do other forms of outputs. This says a log of events, a KML if specified. I don't believe that functionality actually works properly right now. But there are different ways of generating the output file if you want them in different forms. If you want just the XML format, or if you want the volt dump in the column separated variable, or even just a recorder in like a column separated variable or something like that. So this is just kind of a condensed version of the XML output we just looked at. So you can get the power specified on that particular node and then the final voltage that it's solved for. This one's in rectangular form instead of polar form. Same answer, just different representation. And then for like the transformer, if you wanted to look at how much power was going in and out of the transformer, you can see that there is a little bit of a power loss on that particular transformer. So if we want to look at a time series, this is where a lot more of the interesting things come out. The static power flows they're useful for, especially if you want to do like a peak planning study and you know exactly what your peak load is. But if you want to get more of the time evolving behavior, and especially a lot of the stuff that GridLab is used to do the analysis studies for, things like demand response techniques or conservation of voltage reduction, things like that, obviously you're going to want a time series out of those. So obviously an XML file is not practical. Even with a 1 minute time step, you'll end up with 525,000 solutions. So looking at that many XML files, if you could generate that many, I don't think it'll actually let you generate that many. It would be very difficult. So the idea is to use recorders instead, and they'll capture the time-varying behavior and put it into a nice CSV file that you can process. So I think we're into the exercises now, and we actually already did the first exercise. I didn't realize that was the first exercise. So exercise 4.1, and then we'll kind of progress through these. But are there any immediate questions before we start kind of letting it go into a free-for-all and trying out the examples for yourself, or any other questions you have?
Frank, this might be a good point to get a question that came up about how to load.
Oh, yeah.
And how you could separate that between house and residential level, i.e. like with the Zipp Load and a load shape.
Okay.
Does that make sense?
It's an awfully complicated example that's not in here. But, yeah, we can make that work.
I think just showing the object load example and then talking about how that different.
Oh, okay. Well, we can actually put both of them in here, and we'll just keep modifying this IEEE 4 node until we're sick of it. I'm going to change back to the Newton-Raphson method just because I prefer it for personal reasons. So the first thing we want to do is, if you wanted to do like this object load, if you didn't want this to be a static load all the time, if you had, say, some measurement data that you wanted to include. So the best way to do that would be with a player. So we'll make sure we get our module tape in here, which I believe was covered in the first class, but I'm not positive. So we'll put that in there. And then in order to change these values, we'll actually create a player, and we'll just adjust one of them just for simplicity. But if you had a measurement file of, say, the power consumption on phase A at whatever this load represents, you could do an object player, and you have to tell it what object you're going to be adjusting in this particular case. So doing load 4, tell it which property you want to play into. And we're going to be doing constant power A, and the file where everything is in there. So we're going to create this file, and we'll call it load 4 power A values. And it doesn't matter what extension you put on it, it expects it to be in a particular format. And you can also specify a loop parameter if you wanted this to repeat. We're only going to let it run through one iteration, so I'm not going to worry about that. But from a GLM perspective, this is all you would need to do in order to get this constant power value, or constant power A, to be, say, like a measurement point of aggregate load. And then if we want to actually create the player, we'll have to know when this thing starts. That's always a good. So we'll start with that timestamp, and unfortunately, I think this is still subject to a lovely bug that we fixed in 2.3. I think this has to be 3 o'clock in order for it to really work. And we'll give it a comma. This is basically a comma-separated variable file of whatever values you want to play in. So we'll start with the initial value just to be consistent. And then at, say, we'll say at 8 o'clock in the morning. And this could obviously be a lot quicker. This is just a quick, simple example. Maybe we want to change this to half the load. I am not going to divide this by 2. I'm going to round. There. Close enough. And actually, I already screwed up. You don't need that semicolon. So we will save this. Well, we'll save it to the same file name, but I don't remember what I said the file name was. Save it to the player file. So this player file is what it's looking for right here, and it'll play that value into this constant power A. Now, since we're doing a time-varying simulation now, obviously the XML output is not going to work, so we'll want a recorder as well. And it operates fairly similar to how the player works. In this particular case, we'll look at 3 of them just to show you that the other 2 aren't changing, but if you apply to player, you could make them change as well. This will also highlight one of the shortcomings of doing it this way and then using it in Excel. But a file, we'll call it IEEE 4 out time series. We'll just call it CSV. And then interval is the other important thing inside recorders. If we wanted to force this thing to update every 1 minute, we just put 60. So every 60 seconds, it'll drop a value. I'm actually going to use a shorthand notation we have of -1. That'll actually update it every time there's a change. So since our player file is only changing basically between 3 o'clock and 8 o'clock, we don't want to run the 5 hours of 1 minute time steps in between there. That'll just You could. There's nothing wrong with that, but for this particular case, it'll just make it run a little quicker and give us less data to look at. Then you just close that, and now if we run it, assuming I know how to type, this should work. And again, nothing really fancy on the output, but if we look in our output folder here, there should be now this IEEE 4 out time series. If you open that up in Excel, you see it is not the best form, but if you look at the time stamps, these coincide with what we had on our player file. The 3 o'clock in the morning and the 8 o'clock, we changed that load. So if you had this as a measurement data file, you could easily put that into your load object and do a time varying load that way. Now that is if you're doing kind of the a time variant static load, I almost want to call it, or just a time variant load, not really a state load. Say these particular values were actually represented by a neighborhood of 1,000 houses you had or something similar. You can easily go in and change. I'm actually going to close that, otherwise it will yell at me. We'll get rid of this player, and instead of a load, we'll get rid of the load and the player. We don't need that anymore. Just an object meter. We'll call it load 4. That doesn't really make sense, but voltage, otherwise it'll get mad. And this particular case, we'll want the recorder to go, but the properties have changed since we're not looking at a load anymore. So just to be simple, we'll look at measured power. So this will change that load, so now it's just an ordinary node. Now in order to attach a house or a population of houses to this, we have to step down the voltage first. So what we'll need to do is we'll need to get our transformer and our transformer configuration, and I'm going to just copy and paste them just to be lazy. So we're going to specify a new transformer type, and this will be for the split phase center tap. And we'll call it TC single phase center tap. And the ratings obviously are not going to work very well. We will change this from 2400 volts, which is, these initial values were actually the line-to-line values instead of the line-to-neutral. We'll change it to the line-to-neutral. Again, this is just that taps ratio and how it affects the transformer. So obviously putting in the wrong values but the right ratio will give you roughly the same answer, but that will impact how your impedance values get translated. So just something to be aware of. And since this is a distribution system in North America, we're going down to 120 volts. We'll leave the resistance reactance the same just because. And I'll get rid of 2 of these. Rating. And now we'll go ahead and we'll steal the transformer just to change it, just so we have a template to work from. Down below, we have to give it a new name, otherwise it will yell at us. The phases are going to change since we're going down onto the secondary side of everything here. And for the North American system, we have to put an S in here to specify that it's the split phase center tap. Or to a new node we're going to create called house node. This configuration just has to match what we had before, which I believe was TC-SPCT. So now we have that transformer in here, and houses by default will only connect to a triplex node. So we have to convert from the three-phase network that the meter is on, and that actually reminds me I left off. It would have, of course, yelled at me if I didn't do that, so for convenience, we're going to leave it off just so you can see what a nice little error out of GridLAB looks like when it yells at me. Something just to note on there, GLM files follow kind of a C-type notation, so if you want to comment on a line, just put 2 slashes in front of it. And then specify a triplex node. So we'll specify the phases as AS. It has to match the transformer up here, otherwise it'll yell at us. We don't have to give it a name, but we will just for convenience. Actually, we do have to give this one a name because it has to match where we're connected. I misspoke. Nominal voltage, 120 volts, and that's all we need for that. Now, since I haven't added it in yet, we want to do a population of houses. And yeah, that's right. You have to know how to spell. And we'll go down here, and we'll add in a population house, and this is kind of a shorthand way to do it. We're going to get just a random population here. So not the best way to do it, but it's good for this example. And we'll parent this up to that house node. And this is going to give us just a random distribution of the parameters inside the house, which you guys will go over more in the residential module. But this is just a way of basically taking that original static load we had, we changed it into a time-varying load. Now say you wanted to do an aggregate population of houses. This particular case, we're only doing 100 of them. All right, I've just been informed that this does not attach to a node. You have to do a meter. Shouldn't matter, but that's just a particular constraint we have in the house itself. So now if we run this, so it's the exact same thing. We'll probably see a little bit more. Oh, actually, that's right. I left an error in here so we could see. So this particular thing will go through and it'll say object overhead line 1, 2. If we would have given it an actual name, it should yell at us a little more specific. It says it has a phase mismatch at one or both ends. So if we go to overhead line 1, 2, which it's kind of weird. Which one is that? It should be the transformer that's yelling at me. Why is that? Well, this is unexpected. This is not the error it should have been giving me.
Oh, you didn't get phases.
Yeah, so it's actually this one. So if I give this a name, it should be more specific. So OG. If you recall earlier, I left this thing commented out just to show you what an error in GridLAB looks like, and you can see that they are not always the most straightforward error to track down. So if we do this, now it'll tell us overhead line 3, 4 has the phase mismatch. And the reason it has a phase mismatch is because we didn't specify the phases on the other side. So sometimes the error messages aren't quite exactly what's wrong with the system. I mean, this thing's saying there's a phase mismatch because one side has ABCN and the other side technically has nothing because we commented it out. So as soon as we put that back in, it should run. Yep. And we get something about a warning message repeated one time. The simulation may not have actually ran very long because I think we'll let it run for a day. So now you can see that the time is ticking up as it's going through, and then eventually you'll get to the end. Again, nothing really spectacular on the output. You have to actually go and look at the Excel file here, or the CSV file. And then as you can see, the measured power is varying with time, as the individual houses are changing. So that's basically a way of taking your static load. You can apply either a measurement point as an aggregate population, or if you wanted to turn around and you actually had the explicit details of what that population is, if it's 100 houses, you can go ahead and specify those individually. Or you can even put these down as individual triplex meters and then play in a load to them directly. But getting back to my earlier point that I was going to rant and complain about, one of the bad things about recording it this particular way is this is basically a string. There's no easy way of plotting this inside Excel. You have to split it out. The best way to do that we've found is to either A, use MATLAB or something that reads complex formats, or you can specify some qualifiers on any of the complex values. There's also specific properties within the meter itself. I think there's a measured real power and a measured reactive power, but you can also use this dot notation if it's a complex value and you just want a specific portion of it. So now it's plotted out. Go back to our Excel file. And you can see now we have two columns of the real and the imaginary portion. So if we did a magnitude of these, and there's probably a better Excel function to do this, but, and that of course will give you the magnitude. So if you wanted to plot the magnitudes of these, now it's a lot easier to do since you don't have the degrees on the end. And you can see the load is varying throughout the day just with whatever those houses happen to be, just 100 houses on the system. So I think that basically answers the earlier question of how could you do that with different objects. I guess I didn't directly cover schedules or load shapes. Okay, so I guess schedules and load shapes were covered before. The main thing is I can never remember the schedule format, so you guys would have to sit here and struggle through me trying to remember how to actually put it into a schedule. So I'm going to save you that pain for now. But this is basically exercise 4.1, and then we've kind of modified it several times to put different objects on. The object house, again, that'll have a lot more detail. There's a whole slew of properties that go underneath this that you'll get into under the residential module. These are just some default randomized houses. And if we wanted to put more, you know, we'll put 10,000 just to see if we can break it. Something, just to show you guys what it does when it gets angry here, is you'll see something right here, this recorder file, IEEE out, TSCSV, permission denied. That's because we still have it open in Excel, and Excel won't let anything else write to it while it has it open. So you have to close it if you want to get new outputs. Now, as you can see, since we now have 10,000 houses, the simulation is not running very quickly. Now we got 1 second, 4 seconds, 7 seconds, so this could obviously take quite a bit of time to get even a day's worth of simulation, let alone a year. And this is only a 4-node Powerflow. Most of this is actually being done inside these houses. So I don't know if you guys have been shown the minimum time step stuff. Oh. Well, we'll include it in here real quick. So in this particular case, it'll tell it that GridLAB-D, rather than advancing at the default of 1 second, it'll force it to update only every minute. And you'll see that the simulation speeds, assuming I spelled it right, I don't know if it has an underscore on it though. Let's try it. Obviously I'm doing something, oh, I know what I did wrong. There it goes. I forgot the equal sign. I did a space instead. But it'll initialize everything. That'll still take a while. But afterwards, the simulation should start going a lot faster. And you also see there's kind of some warnings about things being outside the anti-voltage limits. That's just a particular warning we have in-house. It's a little slow and it's a little upset just because I have way too many houses on this. This was a nice, compelling example of why you should never do this. Basically, we hit convergence failure because that many houses at 1 minute time step, they're all trying to update, and they're all basically probably turning on their HVAC units, and they are overloading the feeder, especially since we only put them on phase A. We didn't spread it across all 3 phases. So this system is extremely unbalanced and extremely overloaded, so obviously it's not very happy. But if we go back down to 100 houses, which we know worked, we should have much better. See, and there it already ran the day. We're done. So obviously that minimum time step can be very handy for speeding up your simulation, especially if you really don't need the 1-second resolution data. If you're only interested in 1 minute, or if you're matching against like AMI data or SCADA data or something like that, where maybe you have a 15-minute interval, you can change that as well. We don't really recommend going above the 1 minute minimum time step. If you are trying to match against SCADA data or something similar, you'll go ahead and change your recorder interval to be like 900 seconds or 15 minutes. That'll change your simulation rate as well. As you can see, that took a little while longer. If we change this back over to 60 seconds, so it records every minute instead of every time there's a change, goes a little slower. You can actually see it processing there. So just some things to keep in mind. I'm definitely always of the thought process that more data is better than not enough, but there is a trade-off there of if it's going to take you 2 years to get the more data, you'll probably want to constrain it down to just what you really need for your system. Obviously, every recorder has its own set of file I/O operations, so if you have 20 recorders on your system, it's going to slow it down that much as well. Let's see, we had a question about load, and I think it's about the newer functionality that we haven't really covered in here.
So Aaron, this is kind of go towards your question. This might be a little bit easier way than the way we just showed you. So for example, what Frank was talking about before was kind of using these constant power and constant current values up here. But we've also made it so that you can do base power. So you can set the base power for each phase. That might be the SCADA output that you're looking at, or P and Q. And then you could set a power fraction for each of those components, so you can turn it into a Zipp model. So it would be a little bit more direct way of kind of specifying that, so you don't have to rely on just constant power loads or do any of the conversions that are necessary for different voltage levels.
And you can mix and match those too, just to, like if we go back to the, well, I deleted the original example. Let's see if I can get it back here. Lots of undos. All right, so this should be the original file, which it is. So you don't necessarily have to use just the constant power A, constant power B, constant power C. If we wanted to, we can actually change this to match that format. It'll be a pretty contrived example, but still valid. So say we wanted to change phase C to use that notation instead. We'd use, keep coming back and forth here, so it's base underscore power C, and we'll give it the base power. And then we'll tell it that the power fraction for C is 1.0, because we want it all to be constant power. And I think that'll work. That should work, because we're only specifying one. Otherwise, we'd probably also have to put in a power factor C, or PFC, or whatever it is. Oh, power PF underscore C. If we wanted to specify the power factor, so if we only had an overall consumption value here, and we were splitting it out to the different impedance fractions, current fraction, and Zipp fraction, so the percentage, and then also the power factor, you might need to have in there as well. But since we're only doing one, it should work with just this. If we run this, this is back to that original example. So we'll dump it into a CSV file. Or an XML file, sorry. And apparently I screwed something up. Line 121, I forgot a semicolon somewhere. But I'm not seeing where. Oh, I know what it is. That's why we need the power factor. Okay. So, I don't remember what the magnitude of this is. Stupid calculator. So we have to figure out what the overall power consumption of this is, and then we'll specify the power factor. Why am I doing this way? This would be a lot easier if it was in this format by default, but since we're kind of converting between the two, it's a little more difficult. So don't let this be a deterrent. So if we do sum of the squares. And lucky for me, Excel is more clever than I am. Oh, well, isn't that convenient? All right, so if we wanted to specify this properly, we would do a base power C of, what is that, 2 MVA. We do a power factor of C of 0.9. That should work. Basically, it was mad before because I was trying to feed a complex value inside where it's only expecting a double value. But now if we looked at these, the comparison of the two, and the problem here is I don't remember which one of these we actually ran when, so these numbers may not match. We'll see if they do anyway. We'll do this an easier way. And the best way to show you guys, but this is how I always do it. So if we go down to that particular load, we'll see that even though we specified the power on phase C differently, all of the numbers are ending up the same. So you can mix and match your notation here. And use the base power form instead of the constant power form. So whichever one's more convenient for you to apply. And I guess that's just something to point out here real quick. The reason that failed is originally I was trying to put in just a straight up complex number. If you look under mod help, it'll tell you what the type is it's expecting to go into a particular field. In that base power field, it's only expecting a double, which is just your ordinary floating point number, instead of a complex like the constant power C version is up here. So that's why it was yelling at me before, just to clarify that. Are there any other questions or anything right now, or? Otherwise, I might move on from the 4 node onto the 37 node.
I see some questions getting typed in here, so we'll hold on just a second here. So Frank, this question is it possible to influence the power factor C with a controller from the market module?
That's a good question. I would say no, not directly. You'll probably have to put like a runtime class or something in between that will be monitoring. Well, is that me? Oh, okay. I thought that was me. I'm like, sorry. You'll have to create like a runtime class or some type of intermediate class that would look at the market and basically interpret the market prices and then go ahead and influence the power factor C. So it could be done, but you'd have to have an intermediate object or some form of interpreting object that would do it for you. There's no direct tie between module and load that I'm aware of.
Looks like there might be
Hi, Frank. Frank, I have a question.
Okay.
If a circuit does not have a unique solution, what will GridLAB-D compute? Which solutions will GridLAB-D compute?
The solutions you get on the output will be whatever the last PowerFlow solution was. That's actually what we saw up above here, where I had the 10,000 houses on one particular phase, you'll basically get this message right here with the convergence iteration limit reached, and then it'll fail out. If you looked at any of the output files, it'll either give you no answer or it'll give you the last valid portion of that power flow. So if we looked at the XML output of this, when it failed right there at 3 o'clock in the morning, 1 minute, it would give you whatever the very last power flow iteration was. So it would be basically a garbage answer. So.
Sorry, let me make sure I understand. So let's say if a system turns out to have 5 solutions, non-unique solutions, then GridLAB-D will compute all 5 of them? Or
no. If you're... I'm having a hard time wrapping my head around a point where there's 5 unique solutions to a particular power flow, but in that particular case, I honestly don't know which one it would give you. It would give you whatever one it arrived at first.
Okay.
Right. It's going to treat it just like a standard Newton solver is. Wherever it's going to arrive at the local minima rather than trying to find the global minima, unless it can jump itself some way outside of that local minima. Right now, we don't have anything that tries to make it do that jump and get into a different minima. That said, at least in all the simulations that I've run, I have never actually seen it not come to the correct solution. And the reason being is because you're doing this time series again. So your initial solution is actually the solution of the previous time step, which is almost always a marginal fraction difference from the last solution. So you're actually always moving from one steady solution to another steady solution. So it's very rare that you would actually get stuck in a local minima like that.
Something you can do to prevent it as well, if that really was a problem, is you can go in and tighten up the convergence criteria, and that may help bump you out of that local minimum as well. But as Jason mentioned, we pretty much haven't ever really had a problem with that. It always converges to the global one.
Okay, thank you.
So I honestly don't really know what would happen if you were in a state where it got kind of stuck in a local minima. I guess it would just give you that particular solution and not be the wiser.
All right, any other questions? Otherwise, we'll move on to the next examples here.
Well, I think the next one inside the slides is 37 node. And this originally was my mean example. We'll see how mean this version is. Because as the slides say, there's a missing line. And at one point, the GLM actually didn't tell you which line was missing. You had to find it. So I think that's been fixed to be less draconian, but we'll find out. First, I have to get to the folder where it is, though. So then if we open up the 37 node example, hopefully this one's broke. I guess we'll find out. Let's just try running it. I'm a little concerned that I went to the solutions folder, so it might not actually be broke here, but nope, it's not. All right, I went to the wrong folder, so don't do what I just did. So we'll go back where we were. Okay, so this one fails because something's upset. And the best one here is all nodes were not properly populated. This is using the Newton-Raphson solver. I can tell that immediately. However, as usual, the error messages are not the best in the world. So if we open up this particular file, we'll see it has all this stuff specified at the top, and somebody was nice enough to put a comment in there telling you which line is missing. But if we scroll down far enough, I think it actually says somewhere in the comments as well. I guess not. There used to be a one-line comment down here somewhere saying which line was missing. Maybe we moved it up here. But basically, if you look for 729, you see there's a load, and 744 should be another load. There's just a couple other lines going off of it. And if you look at the topology for the IEEE 37 node, this will make a lot more sense. Basically, the reason why it's not solving is because we're missing a line. And unfortunately, as you can see from the error message, it doesn't really tell you which line is missing. So there's a couple different ways of finding that out. If it wasn't explicitly put on the top here, I'll actually show you one of those just because it's always nice to have. And then I'll show you what else happens when you use a different solver method. I have to remember this. And fault check is actually an object that's more associated with the reliability module, but it does have some interesting functionality that's useful for debugging your models inside Newton-Raphson, especially when you're getting that either all nodes cannot be populated or if you're having a singularity value return. So if we look at the different parameters here, we'll just copy all of these. So there's a couple of functions, reliability alterations and handle sectionalizers, which we don't care about. The enumeration for a check mode, so you can actually tell this to go off on every single Powerflow solution if you want, but we're not going to do that because we only need the initial one. So we'll just say check mode single. And we specify an output file name. And then the reliability mode and the event gen object are things we don't need to worry about. They're associated only with the reliability module. So this should be all we need to run this. And it'll still fail out, but it'll give us an output file telling us some indications of why it failed out. Well, it would, except for what's missing. Okay, so ignore everything I just said. This particular object is only really useful when you have a phase mismatch or you have a singular matrix condition. The particular error we're getting here where it's telling you not everything can be populated just basically means that there's a connection missing somewhere, and that's why not all of your nodes are getting done. It has to do with the initialization sequence inside GridLAB-D. So we'll actually have to fix this to get it to work. I'll show you where this is actually more useful here afterwards, but I'll show you a second kind of problem. This is one of the downfalls of the forward backsweep algorithm. If we turn around and run this in forward backsweep, it runs. And everything is hokey happy dory. The difference will be this particular node has now become an implied swing node. So if we look at our output file, oops, that's the wrong output file. And this is a different way of finding out where you have like islands on your system or other problems. So if we go down here and we look at the swing node, you'll see it has a particular nominal voltage, which is very odd. But that's because this solver isn't quite modeling the system right. But if you find out what the nominal voltage is here, so it should be 4,800 volts. So if we go in, oh, I know what's going on here. The reason why these numbers are off, they aren't nice round number values, is because we manually put the first point in the system. I believe this particular GLM file is lacking the regulator that's actually on the top of the 37-node system. So the swing node on the system is actually the node below the regulator. That's why those numbers aren't nice round nominal values. But regardless, the approach will still work here. So we know the nominal voltage on most of the nodes on this system is 4,800 volts. So what we can do to find out where the breaking point is we can find one that looks like it's setting itself to the nominal voltage. And we know kind of in advance that this is actually a load, just because that comment on the top says the line is missing between two of the loads. But we can go down here. Once we find the voltage column, there it is, and we'll look for any of them that have very nice round numbers. Like this one. That is very suspicious that they have exact numbers for the degrees. So if we go over here and look, this is going to be kind of hard to do. We find out this should be like node 744 or 729. Is that the right one? Okay, 729. So that's the other side of the connection point. So without that connected, forward back sweep is basically assuming this is a new swing node and it's resetting. So you'll still get a valid solution out of this, but it's not really the solution to the system you really wanted. So that's something to be careful between the forward back sweep and the Newton-Raphson is. Newton-Raphson will give you some cryptic error messages when your system isn't completely connected, but it won't solve it. Forward back sweep will tell you absolutely nothing and solve it just the same, and unless you explicitly notice that you have an island in your system, you probably will never notice. You'll get the answers, they'll look semi-reasonable, and that'll be the end of that. So now we want to put a line in between 729 and 744, so I don't particularly know how long it was, so we'll just copy one of these and steal it. If you wanted to know how long the original line was, we could actually go and look inside the IEEE 37 node spec. For the purposes of a quick demonstration, we'll just directly. And these particular were both loads. So the length we'll leave at 600 feet. The configuration is basically the same as most of the other lines in the system. Now if we run this again, it should still, and it runs just fine. And if we look at the output, if we look at node 729, you'll notice the voltage now is not a nice round number. Once we get over there. That's kind of the downfall of looking at the XML file this way, is especially for things like loads. Some of the more relevant information is all the way over on the right, and you have to scroll for a while. So as you can see, they're not nice, ideal round numbers anymore. So it is solving the whole system. Where the fault check object is particularly useful is if we take our 729 example, and say we only put phases A and B in there. We didn't put phase C. So there's actually a disconnect between phase C on node 729 and 744. Now we apply the fault check. Well, if we don't have the fault check in there, it should fail, and it should basically tell us the same error we had before. It'll tell us, well, this one will tell us it can't converge at an operating point. This is an indication that there is a singular value in the matrix, or your matrix is singular, rather. It can't invert it. So if we want to find out an idea of what's causing that problem, because one of the most common things that causes that to happen is either like an open switch or a missing phase on something. So if we run the fault check, it still fails, but it tells you there's an unsupported phase on node 729, which is the one that we just removed it from. But if we look at the output file, you can see that on that particular load, so that must be the end of one of the branches, phase C is unsupported. So that'll help you track it down, and basically if we went in here and we looked for node 729, we can find out all instances of it, and we see this is an ABC delta connected load, and we see this particular line is only an AB, and those are the only two instances, so this is obviously the issue. We convert that to have the C phase, then it runs fine, and that output file is empty. So that's where that fault checked object is a little more useful. It's mainly for the reliability, but if you're getting any singular matrix problems and you suspect they might be related to either a line missing or an islanded type condition, this is a good way to track them down, unless that is a hard break islanded condition, in which case you'll see the first message we got where it says that not all nodes have been populated. And that's a little more difficult to track down. The best way we usually do to figure that out is exactly what I showed you, where you put it in forward back sweep, and then you go look for something that has a nominal voltage where it shouldn't. And that's a good indication that it has made that a secondary swing node, and something's missing connection-wise, or you actually have two systems in your file instead of one. That is an error right now in Newton-Raphson. Conceivably, we'll eventually get Newton-Raphson to work with islanded systems, so that may not be an error in the future. It may start giving you basically the same result for backward sweep would, where it'll imply a second swing node, and you'll get two sets of answers, and unless you realize that you accidentally segmented your system, you'll get what looks like a valid answer. So just something to be aware of.
So I wanted to come back to a question that was on the chat here a little while ago that I forgot to come back to because it was a really good question.
Okay.
And the question was about how to, basically, all this sounds great if you're going to create like a single load or a single house or anything like that.
Mm-hmm.
But the question was, well, I want to do this with 1,000 or 10,000 or 100,000 objects.
Uh-huh.
And so basically I wanted to come back and kind of touch on that a little bit was the fact that the way that we've gotten around that right now is that we use some kind of scripting format, either MATLAB or we have some external folks who are working with some Python scripts that are going to be kind of addressing that issue. We've put all of our MATLAB scripts out on SourceForge. You can find them under taxonomy feeders, is I think the main root folder that it's part of. And really what that is it ends up being a text parsing script. So MATLAB was probably not the best tool to use it with, but it's what, quite honestly, it's what I'm familiar with, so that's what I worked with. But in the end, whenever you're creating something of that scale, just don't see any other solution than creating an external script to kind of create that model for you. Something that's a object-oriented text parser might be something more in line just because of the way it lines up with this tool. So creating it in Python, which is coming from, like I said, some external collaborators that they'll be posting up probably in the next month or so. That's a little bit better solution than the MATLAB ones that we have out there. One, because MATLAB treats this all kind of as a linear solution, while the Python scripts would treat it more as a object-oriented solution. You could go in and do things like, I would like to take all 100,000 houses and increase their load by 5%. Whereas for us in the MATLAB script, that's much more of a linear problem that you have to kind of solve, and it's a little bit of a pain. But really the answer is I don't see any way around it except for doing some kind of scripting language outside of GridLAB to create the model file that you want to put in.
Whoa. The alternative to that, if you're doing a very simply connected system, but you have a lot of houses, if you don't want it to be deterministic, you can basically do how we did on the 4-node system, where you can do like the house, the colon, and then ... 10,000 or whatever. But for most realistic simulations, that's not a very good approach to it, just because since it is randomized, you'll get a different answer every time you run GridLAB, basically. Oh, that's your answer, so I don't have to answer that one. There's always a good chance. Do you have funding, or are you willing to do it yourself?
Jokingly, yes, but that's something we've been trying to address in version 3.0, which is not even going to be branched off our main development trunk until, I would guess, probably February or March at this point, sometime after 2.3 gets released. And it's effectively an HTML or what we're called server mode-based API. That's actually what the Python scripting actually accesses that API to pull the information down. So it does things like goes in and grabs all the objects and grabs all the object variables, and then allows you to access those externally. So, yep, the answer is it's in development, but you have to go to the more experimental version than what we're talking about here. And that version 3.0 is, like I said, we're scheduling it to start branching off and becoming a stable version here about, I would guess, January or February. with the goal of releasing it as a final release version, full executable sometime in the end of summer.
If there's any more immediate questions, I'm going to plow forward on the examples here a little bit more. So now we have to go ahead and change this line into a delta-delta transformer, just because. And this will be a very unexciting transformer, just because we're going to have a 1-to-1 voltage ratio, just so the system doesn't yell at us. But we'll get rid of that fault check object. So in the grand scheme of cheating here, there is another transformer in here. Once you learn how to spell. I am going to steal it, and then just adjust it. So then if we go back to the line we put in, we'll get rid of this line, and we'll replace it with a delta-delta transformer, which happens to be what type 2 is, but we'll explicitly write it out here. Call it new, and again, giving it no turns ratio. Just to show kind of the similarity of these two, I'll basically copy this and just change it. So this will now become a transformer. We'll give it the same name. Transformers don't have a length. And in the configuration, I'll just change to transconf new. That should be all we need to do to replace that line we just added in there with a delta-delta transformer, and in this particular case, just with a turns ratio of 1-to-1. It runs, and if we look at the output, the answers be pretty unspectacular. The biggest difference is that node 729 maybe is slightly higher voltage now, just because there's not the line drop associated with the underground line that was between it and line 7 or node 744 before. But otherwise, the answers should look pretty much identical. And they don't look unreasonable, and the fact that it didn't yell at us, so that's a good indication that that was a success. So now just to highlight kind of a zero-length line connection, we want to connect an additional load via node-to-node, and we don't really specify which one of these we want it to be, so we'll just pick an arbitrary one. Basically, I'll go find the first node I find here. Must be down. Well, I'll do the second node, because attaching a new load to the swing node is not very exciting. So we'll just attach it here to node 702, so we'll just do an object load. And this is just like what we did on the 4-node system in terms of the overall specifications, nothing special here. Give it a name, give it a nominal voltage. The nominal voltage in this case has to match the parent, otherwise it would give us a warning message. So then we parent it to node 702, which is this one right up here. And that's basically, this load will be applied at the exact same point, the exact same bus on the system, but as a modeling convenience, we want this load to be separate, just so we can explicitly put it in there and not wonder if it's actually influencing the power flow in a different format, or if it's a lot easier to control this way. Or in this particular instance, if we want to add in a load after the fact and we don't want to go find every instance of node 702 and change it to a different name or anything like that. And we'll give it some specifications here. We'll put just a small load on here, just so it doesn't yell at us. And I am doing this in the traditional format, not the new one we talked about, just out of habit. You could do it both ways again. Just give it some arbitrary load. And I guess another point while I'm typing this in here is you are not constrained by using the J electrical engineering notation for complex. You can also use an I. Theoretically, that's all we need. So by doing this parent and that connection there, we're implying the 0-to-0 connection point. Run it. It tells me that I did something wrong. So this is good. Mainly because I can't spell. Should be phase, not phase. Now it ran, and if we looked at the XML output, it'll give us a new set of answers. They'll be slightly different. Unless we were doing a direct comparison, it would be pretty hard to see the difference in these answers just because node 702 is fairly close to the head of the feeder. So you're not going to see a lot of big fluctuation in the voltage as a result of adding that load. Plus, we added a really small load. An alternative way to do this, just in terms of GridLAB-D syntax, if you don't want to use the explicit parent structure here, you can actually embed objects. So we can do this, copy this directly inside the node. The big difference here is this does consider it to be a property line now, so you do have to put a semicolon on there, otherwise it'll get upset. But big difference here is I removed that parent line, and it has an implied parent since it's inside this overall object now. And just for giggles, change the XML. Any of those output parameters you can specify with a set command up here in the top of the GLM. The biggest difference is the names aren't always the same. If you remember from earlier, I was using --out file, or output, I believe. Up here it's called save file. So that's kind of the disadvantage of using them in here as opposed to the command line. The syntax doesn't always match, but you can access any of those parameters on just any of the command line parameters from inside the GLM as well. They just don't always have the same syntax. So just something to be aware of. So this is effectively doing what we did with the 4-node with the out file. It's just inside the file, so you can change it a lot easier. So now if we look at these, it should give us pretty much the same answer. Now, this section, obviously there's some differences just because of how things get loaded. The XML file actually includes a lot of information about how objects are put into their different ranks in GridLAB-D and what order they're executed, which does get shuffled around a little bit. But after that, we look at the answers. All of the differences we see are on these power values, and you can see it's a difference of 3 nano VA to 4 nano VA. So it's basically numerical error inside the solver. It's not an actual different solution. It's just how the thing happened around on that particular inversion. But if we get down into the actual solver portions, you can see there's no red over here on this particular comparison program. So all of the answers are identical. So by doing it explicitly with the parent, or wait, that's the wrong one. Or by implying the parent by putting it inside the other object, you get the same result. The only caveat to this that I will point out is you can do something like this with the configuration objects. So for like an underground line, instead of doing configuration, line configuration 7211, you could put configuration and an object line configuration in here and specify all the parameters. The problem you get into with that is in this particular version of GridLab, it's something we fixed in that newer development version that Jason was talking about earlier. It will initialize things in the order they're loaded, and if you embed the configuration for lines and transformers inside the object like this, it actually gets initialized after the line object does, and it'll cause some problems with your analysis. It'll give you some really weird looking values. It'll say something like the power is outside its limits of pound indeterminate or something like that. If you ever see things like that, it's probably implying that you have a configuration inline somewhere. So what we do to prevent that problem, just kind of as an aside here, is we typically specify all of our configurations up near the very top of the file. The alternative you could do if you don't like them being on the front of your file here is you can put them into a separate GLM file and then just include it at the top here. And you could basically create a library of line configurations, line types, and everything like that, and then include it in all your GLMs, and have them referenced a lot easier that way. But just something to be aware of with the parent-child restrictions. You can conceivably put line configurations and things like that inside there, but up until the 3.0/trunk version that we're still working on, it'll start to give you really weird answers on your output, so be careful with it. So that's all we have for the 4.2 exercise. Are there any other questions kind of related to that, or do we need to take a short break again, or otherwise I'll plow on to the 13-node system example. Okay, onwards and upwards. So we go on to exercise 4.3. So this is an IEEE 13-node system, but we've attached a lot of houses to it. So a couple things we want to do is we want to look at the interface between the Powerflow module and the residential module with the triplex meter. That's actually what we already kind of did with the 4-node system when we were showing the different ways of adding in your aggregate loads, either with the load object or with the 100 or 10,000 house example that I tried putting together. So if we load up the system, I don't think it's in this folder. I think it's in a different folder. There's this particular one. Going back to an earlier question, this is how we do the larger generations. This is a much earlier form of the script than we currently use. There's a much better version up underneath the taxonomy feeders folder that Jason mentioned earlier. But this is how we've generally populated feeders or created more advanced systems with a lot more houses in a deterministic ways, with a MATLAB script basically that parses out the text file and then generates a new text file. So if you want a very simplified example of how we do that, there is one included in this module under the IEEE 13 node, but the much better example and the much more robust example is up underneath the taxonomy feeders folder on SourceForge. But if we run this one, let's get so the particular file is probably IEEE 13 mod. Another warning you might see from time to time, especially if you're using older files, is this one right here. This 632 to 635 does not follow strict naming rules. If we look at this particular IEEE system, this is a very simple system. It's using this colon notation for all of the object names, and then it has numbers for the individual names and object references. GridLAB-D used to support this. We highly discourage it now. Basically, you have to put this set relaxed naming rules on the top of your file. GridLAB-D is expecting all of your object names to start with a letter of some sort. So instead of this being 632 to 645, you'd have to put like 632 to 645. It just has to start with a letter instead of a number, and that's just part of the parser thing. You can override it, but we recommend you don't, and we kind of recommend you don't use this colon notation anymore either. You actually assign an explicit name. So instead of saying like line configuration 603 right here, we'd give it a name like we did in the 4-node system, where it would be like OHL configuration 604 or something like that. They both work, but this one is not the preferred format. And unfortunately, I was in the wrong folder. As we can see from this file, it's very short and there are no houses on it. This is actually the base IEEE 13 node. It's in this folder. Basically, you could run this MATLAB file on it, and it'll generate the one that we'll actually end up using, which is under the solutions folder. Should be this one right here. Okay, so as you can see, this is a much more complicated file. This is still the 13-node system, but this was generated by that MATLAB file. The downfall of this is it's not going to run where I put it. I have to put it here. Mainly because this particular file, since it's a lot more complex, it's looking for some weather data and some player files. See if I can find them in here. Well, I thought it was, but somewhere inside here it's looking for player files, and those happen to be in this folder. So we could copy these players and everything else out into the other folder I was originally running in, but it's easier just to copy the actual GLM into where we're currently located. So if we run the right file this time, we'll see it gives a warning about the time zone because we probably spelled it wrong. And then it goes through and runs and tells you there's some houses outside of their ANSI voltage limit. And basically, if we look at the original GLM, it just ran this for 1 hour. So not a very long time. But it did generate some CSV files for us. Now, so just your normal recorder output. So this will give us the time varying solution for the first hour of simulation. And this particular one is looking at a bunch of meters on the system. This is actually using probably a multi-recorder based off the formatting here. So a multi-recorder is just kind of an extension of the ordinary recorder object. The biggest difference is your ordinary recorder can only record from one particular object. The complement to a normal recorder is a collector, but it only does overall statistics on a particular object, so if you wanted to, or a particular group of objects. So in this case, we're pulling out the measured power of all of the different triplex meters on the system. If you did it with a collector, it would only give you one value, and it would be like the mean or the standard deviation or whatever you specified it to record. If you want the explicit values, you can use a multi-recorder, and then you specify the object and the parameter this way, and you can get them all into one Excel file, or one CSV file, which is a lot easier for your analysis if you're doing any type of post-processing scripts on it. But the explicit exercise was mainly to look at the interface between Powerflow and residential, since GridLAB is kind of a collection of modules. There are things that Powerflow can do by itself, that residential can do by itself, that market can do by itself, but a lot of the quote-unquote more interesting studies are usually a combination of one or more modules. You're either looking at like residential and market, residential and Powerflow, or even residential, Powerflow, and market, all three of them combined, or even more combined. So the whole point of this was to kind of lead into what I believe the next course is on, which is the actual residential module, and just see kind of how they interface. And that's what we did in the 4-node system earlier, where you'll get down and you'll have the house, which is a residential module object, and it's interfacing with Powerflow via this triplex meter 1. Unfortunately, I should have searched a little different here. So we see up here there's a triplex line that goes between triplex node 1 and triplex meter 1. And then eventually house 1 is connecting to this triplex meter, and that's the Powerflow connection. The residential module is interfacing with Powerflow via this connection right here. It's of course spread across the file, so it's not as straightforward or easy to see, but the same aspect is occurring on each of these other groups of houses. House set 2 is attached to triplex meter 2. Something else to point in here, this is that notation I was using earlier. This will basically replicate this particular house 20 times. So you can see there's some random variations in here for both the Zipp Load base and then also for your set points and your flow rate of your house. That's another way to get kind of your aggregate model or your larger system models without having to use an explicit script. But the problem with this particular one, especially in version 2.2, is you'll get different answers for different randomizers, especially across different platforms. So if you want kind of a semi-random / deterministic simulation where you run it multiple times and get the exact same base simulation that you can compare technologies on, you'll have to either explicitly define each of these houses, or you'll have to use a later version of GridLAB-D where you can not only fix the seed of the randomizer, but also it's a common randomizer across all platforms. Otherwise, doing this particular notation, if I ran this again, I would probably get a slightly different answer, even though it's the exact same system for all points and purposes. So just something to be aware of. I think that's the last portion of the example. Are there any last-minute questions or kind of unrelated questions that are still part of the Powerflow module, or? Okay. That's a good question. I assume you are talking about like an XML schema or something similar to that. You can conceivably, although to my knowledge, it doesn't quite work right, and we found that out recently. I believe it is something that Dave Chaston is working on fixing right now, if I remember correctly. There's actually, I think there's a forum post, it might actually be you that posted the forum question, where we thought there was a way to do it with our Xerces package via an XML, basically an XML output, and we discovered that the XML interpreter wasn't working quite right. So it's something we're in the process of fixing. So conceivably, yes, but at the moment, not really.
We've got a couple more questions coming in through the forum here.
Workarounds are always good.
We've got about 20 minutes left here that we're planning to stay online. Both Frank and I are happy to stay online and answer any questions that come up. So it looks like there's a couple coming through. So what we'll try to do is I'll try to get this posted up and all the information from this presentation up onto the web by the end of this week, and send you guys all emails with all that information. And a follow-up there to the schema different for 2.3 and 2.2, only if there's additional objects or properties added to those objects. So you'll get more fields, but the format itself doesn't change.
And relating to the other question about the SCADA and discrete loads, if I'm understanding what you're asking correctly, you should just be able to put a load on whatever the 2-node of your final transformer is. You shouldn't have to actually put the triplex line and everything down to the final service location. So you can basically do the example we did on the 4-node system, where you take that load and then apply a player to it, and then just feed your SCADA data in directly as the player.
Yeah, Bob, this is going to depend on how much you want to reduce order your model. So you can, you could collapse it all the way up to the trunk line if you wanted to, and just have a straight shot system and attach loads at that point. So you can kind of, hopefully we've made it flexible enough so that you can kind of determine how you want that to look and reduce order it however much you would like to. No, if you are using like that identical configuration, basically using it as a library file, the only impact it will really have is on load up time, so basically how long it takes to read the file and set up the initial model. But once it's going, you're pretty much going to see the same exact performance.
I guess the other thing I would caveat that with is if your file is big enough, if you repeat the transformer configuration every single time with a unique identifier, even though it's the same, you're going to eat up more initial memory. But as Jason mentioned, it is just primarily going to be on the loader side. Once the simulation actually starts ticking off, it won't make any difference.
For the transformer, basically what that will do is if you put the total power rating on there, it will take a look at it and sorry, let me start over. If you put the total power rating but not the three-phase individual ones, then it will divide it individually and equally across those three phases, or vice versa. If you only put the three individual phases, then it will sum it up and put the total power rating for the transformer. So it does make some assumptions and balances it equally, but that's a pretty good assumption for most transformers. If it's easier to ask these questions over the phone, then feel free to unmute yourself from the link service and go ahead and chat. As far as multi-speak, no, not really. So we haven't done any work converting towards other standards. We have a couple scripts available that let us convert between Synergy and GridLAB-D and SIME and GridLAB-D. But we haven't worked on any other type of conversion tools yet, and specifically multi-speak we haven't touched at all. Multi-speak or SIM or any of the other standards. But those, but the SIME and Synergy ones we've made available for anybody out on the SourceForge account if you want to take a look at what we've been doing and how we've used them. So the IEEE 13 node, I would say it originally was, you know, back when Bill Kirsting and a few others created it. I think back in '91 is when it came out. It was very much used as kind of the baseline to say, can different tools do unbalanced power flow in a similar manner, and specifically then can they handle voltage controls? I would say it's probably less so now, especially as some of the newer, larger feeders have been created, say like the IEEE 123 node and the IEEE 8500 node. I would say some of those are probably the more likely ones to be used as a comparison. Even the 34 or the 37 node, just because of the complexity level. The 13 node, at least now, is not that complicated. 20 years ago, very much so.
In terms of an explicit starting node, you just need if you're using Newton Raphson, you just need a swing node somewhere on the system. It doesn't have to be explicitly a substation. It can be wherever you're starting your particular system. So if you wanted to actually start your feeder, if it's a group of feeders that all connect to a common substation, you can start it at wherever the top of that particular lateral or that subfeeder is. Or if it's like a branch halfway down a feeder that you're interested in modeling, you can start from that point. It doesn't have to explicitly be a substation. The only caveat to that is one of the newer functionalities we have is interfacing the PowerFlow module with Power World to do kind of transmission and distribution level interactions. In that particular case, you do have to have a substation at the top of your feeder in order to interface with the Power World stuff. But outside of that, as long as you have a swing node somewhere on the system and it's a node, load, or meter, it doesn't really care where it's at. It'll affect your solution, of course, if you set the bottommost node or bottommost load as your swing node and then let the rest of the solution solve off of that. It'll give you some different results, but there's no real limitation on where you put the swing node, so it doesn't have to be a substation. It can be anywhere else.
So there's, I don't know if I'd call them MATLAB tools per se. In our newest version of GridLab, which again is not coming out until later next year, we actually have an integrated link between MATLAB and GridLab, so that you can do, say, design your controls, and then maybe you want to design a system control, and then you can send in signals into back and forth between GridLab and MATLAB. Say you want to look at the substation load in the GridLAB-D simulation, and from there do some kind of decision about how much water heater load you should shed. But you want to build that optimization and control engine inside of GridLab or inside of MATLAB. We do support that. But then, as far as for standard analysis, maybe Frank, you can hand me back control for a second.
See if I can remember how to do that. I can stop.
Let's see. Sorry, let me get this set up here so I can show you guys what I'm talking about here. Share. Yeah, well, that's coming up. Correct. 2.3 is not officially released yet. It is pretty darn close. There's one more feature we're trying to add in right now, and once that feature is in, we will release it. That's probably scheduled for, I would say, end of December, maybe early to mid-January, right at that point. But let me pull up the SourceForge account here to kind of show you where these MATLAB tools are available. So if I come to the SourceForge page, there's a basically you can do an SVN browse, so you can actually walk through all the code sections and download them individually rather than trying to do the entire SVN download, which is now getting to be pretty massive. So you can come to SVN browse, or if you've downloaded the software or the code onto your desktop, you already have access to this. And you can come into taxonomy feeders, and we have this thing called population script. I'm sorry, there's a lot of stuff in here, but effectively you can see this file called feedergenerator.m. This is a MATLAB script that we've created that accesses particularly our taxonomy feeders, which are a set of prototypical feeders that we designed to roughly represent the topology of feeders across the United States divided by regions. So whether they're Hawaii versus Western U.S. versus the Midwest versus the Northeast. We have different topologies for all these different areas. And this feeder generator.m, if you go in here, and there's a number of subfiles that go along with this that are all .m files also. Okay, so let's view it. So basically what this is, it's a MATLAB script that lets you come in and basically say, I want to look at one of these different technologies. So you can see here we have a base case versus CVR versus, say, time of use with critical peak pricing versus PHV versus solar residential. And then we can do a few things like, okay, which basically we can look at which taxonomy files do we want to look at. So do we want to look at one feeder, or do we want to look at dozens of feeders? If you look at some of the other MATLAB files in here, so for example, there's a trying to find it, sorry, user configuration. You can come in here and you can set up certain configuration files to say, so for example, if I'm the default user, I didn't actually say which user I'm going to use, I can set up what solver I'm going to use, which files I want to actually to do simulations on, all sorts of different things that you can kind of set up, and you can kind of set up your own custom things on there. But really what the goal is to actually be able to, once you get it all set up and get everything in the right location, then really the idea goal is to be able to say, okay, now I've got a single model, I know what the base case solution is, I can run that model, I can get the outputs for it, and now I'm going to run it again, and I'm going to use CVR. And I'm going to use different settings on that CVR to find out what the difference in energy consumption is. So really what this ends up becoming is a set of examples of how to do every single one of these different technologies. They're not the only way. There's definitely other ways to do it, or other control modes and things like that. But this at least will get you started in the right place. What this will do is it will pull in the flat feeder files, which are just pure power flow, goes from the substation down to the transformers, and then it will rework it and add on house models, weather files, recorders and players and all this good stuff. And then it will, where you ask it to, it'll add on these technologies. So it gives you a good example to work from to kind of say, oh, okay, I got it now. And we'll go into this script in a lot more detail, I think, in January when we get to that section. We'll actually kind of dig into it and show you how to use it. We'll pop up MATLAB and walk through its usage. But until then, this is a good place to kind of get an idea of how to get started. So unless there are any other questions, I think we're just about wrapping up here. I don't see any typing on the forum and no questions on the line. So with that, thank you, Frank, for presenting today. Appreciate it. If there's other further questions, don't be afraid to email me, or if there are good open questions for everybody, feel free to use the forums. We try to monitor those pretty actively and usually get answers back to you within a day or two, or admit that we don't know the solution and we'll come back to you later. But we try to address all of them within a day or two. With that, everyone have a great day, and we'll see you in a few weeks with the residential module. Thanks a lot.